What happens when two galaxies collide? How close is Andromeda really? And are we already on a collision course? Can two galaxies become one? Or will everything we know be torn apart? What secrets lie hidden between the stars? From the heart of the Milky Way to the edge of Andromeda, the journey begins now. In the vast silence of space, a collision is coming. 2 trillion stars are on a collision course, moving toward each other at over 400,000 kilometers per hour. Not stars colliding with stars, but something far more magnificent: 2 entire galaxies, each containing hundreds of billions of suns, slowly dancing toward one another across the cosmic void. This is not science fiction. This is the future of our home. When you look up at the night sky, you see only a fraction of our galaxy, the Milky Way. But beyond our cosmic neighborhood lies another spiral of light, Andromeda, larger than our own galaxy and coming closer with every passing moment. Tonight, we embark on the ultimate journey, following a path that spans 2.5 million light years and stretches across 4 billion years of cosmic time. We will witness the slow approach, the gentle embrace, and the eventual merging of 2 galactic giants. 2 galaxies float across the cosmos, spirals of light separated by silence. One is our home, the other is coming closer. Tonight we follow a path billions of years long. From the Milky Way to the Andromeda, what does it mean when galaxies collide? How will the night sky transform as these 2 spiral arms intertwine? And what will remain of our cosmic home when 2 become one? Close your eyes, breathe deeply. Let the stars guide you on this journey through space and time as we witness the most spectacular collision in our cosmic neighborhood, a collision that will reshape the very fabric of our night sky. Imagine standing on Earth 4 billion years from now. Above you, the familiar band of the Milky Way has transformed. The night is brighter now, illuminated by the approaching glow of Andromeda. Slowly, over millions of human lifetimes, the 2 galaxies have drawn closer. Now they begin their cosmic dance. This story begins with a single photon of light, traveling from Andromeda to your eye. That journey takes 2.5 million years light that left Andromeda when early humans were just beginning to walk upright on Earth. Now reaches us. We see Andromeda not as it is today, but as it was when our ancestors first gazed upward and wondered about the heavens. And yet, despite this vast distance, our fate and Andromeda's are intertwined. The gentle pull of gravity, the same force that keeps your feet on the ground, reaches across millions of light years, drawing these 2 giants together. It is a process so slow that 100 human generations could live and die without noticing any change. But in cosmic time, it is happening in the blink of an eye. The stars above us have always seemed eternal, unchanging. The constellations that guided ancient sailors still guide modern astronomers. But this is an illusion born of our brief lives. The sky is not static. The cosmos is not still. Everything moves, everything changes, evolves. Tonight, we step outside the constraints of human time. We will watch as stars drift and galaxies collide. We will witness the birth of a new cosmic structure, neither Milky Way nor Andromeda, but something new, born from their union. Astronomers call this future galaxy Milkomeda, a cosmic child of 2 spiral parents. How do we know this will happen? The light from distant galaxies carries information about their motion. By studying this light, astronomers have discovered that Andromeda moves toward us, not away. Unlike most galaxies, which are carried away by the expanding universe, Andromeda and the Milky Way are bound by gravity, spiraling toward an inevitable encounter. This is a journey not only through space, but through possibilities. What will happen to our solar system? What will become of Earth? Will the night sky that has inspired humanity since our earliest days transform beyond recognition? The answers lie in understanding the delicate choreography of trillions of stars. guided by the invisible hand of gravity. So settle in. Let your mind expand to encompass billions of years. Let your imagination stretch across millions of light years. For tonight, we are cosmic travelers, witnessing the slow unfolding of galactic destiny. From the spiraling arms of the Milky Way to the approaching glow of Andromeda, this is the story of our cosmic neighborhood and its inevitable transformation, a tale of two galaxies and one shared future. The motion of galaxies can be visualized by imagining space itself as a vast ocean. Large concentrations of mass galaxy clusters and superclusters create gravitational wells in this ocean, attracting surrounding matter. Galaxies flow along the resulting currents, drawn inexorably toward these wells. Some galaxies travel in groups, like schools of fish navigating these cosmic currents together. This ocean is not static but expanding. The space between distant galaxies stretches, carrying them away from each other. Only where gravity is strong enough to overcome this expansion, as in the case of the Milky Way, and Andromeda galaxies move toward, rather than away from each other. This delicate balance between gravitational attraction and cosmic expansion shapes the evolution of the entire universe. As galaxies move through space, they sometimes encounter intergalactic gas-vast, tenuous clouds of hydrogen and helium floating between the galaxies. When a galaxy passes through these clouds at high speed, the gas can create a kind of headwind, stripping away some of the galaxy's own gas and potentially diminishing its ability to form new stars. This process, called ram pressure stripping, is particularly common in dense galaxy clusters, where intergalactic gas is more abundant. The Milky Way's journey through space has largely spared it from this fate. Traveling through a relatively empty region of the local group, our galaxy has retained most of its gas, allowing star formation to continue at a modest rate. Approximately one new star forms in the Milky Way each year, a leisurely pace compared to some galaxies, which can produce hundreds of stars annually. The motion of galaxies through space is not merely a cosmic curiosity, it determines their evolution and their fate. Galaxies that travel through dense environments tend to lose their gas more quickly, causing star formation to cease earlier. Isolated galaxies, traveling through emptier regions, often retain their gas longer, remaining actively star-forming for extended periods. The Milky Way and Andromeda have both benefited from relatively isolated journeys, allowing them to preserve much of their gas and maintain star formation for billions of years. But this isolation is temporary. The trajectories of the Milky Way and Andromeda, determined by their mutual gravitational attraction, have set them on a collision course. Their motion through space, once carrying them along separate paths, now brings them inexorably closer with each passing moment. The two galaxies, traveling through the cosmic web, are like two rivers converging, their waters destined to mix. This impending merger is not unique in cosmic history. Galaxies have been colliding and merging since the early universe, their motions bringing them together in cosmic reunions that transform them fundamentally. The Milky Way itself bears the scars of past mergers, its structure shaped by the galaxies it has absorbed throughout its long history. But none of these past encounters compares to what awaits when Andromeda arrives. The celestial dance between the Milky Way and Andromeda is part of a larger pattern of galactic motion and evolution. Throughout the universe, galaxies move, interact, and transform. Some collide violently, triggering bursts of star formation visible across billions of light years. Others gently merge, their stars intermingling like two crowds peacefully flowing together. The particular trajectory, speed, and timing of these encounters determine their outcomes. As we contemplate the motion of galaxies on these vast scales, we gain perspective on our place in the cosmos. The Earth orbits the Sunday orbits the galactic center. The Milky Way moves through the local group. The local group travels within the Virgo supercluster. And all of this occurs within the immense cosmic web that spans billions of light years. At each level, gravity choreographs a dance of unimaginable complexity and beauty. For most of human history, we perceived the stars as fixed and immutable. We now know that the apparent stillness of the night sky belies a reality of constant motion. Stars drift, galaxies travel. Everything flows across the cosmic sea, guided by the invisible hand of gravity. And in this perpetual motion, lies the key to cosmic evolution and the fate of our galactic home. Galaxies drift like leaves on a cosmic tide. Some draw nearer, and none draws nearer to the Milky Way than Andromeda, our massive galactic neighbor, approaching steadily across the void between worlds. These measurements have also revealed something unexpected about the approaching collision. Rather than a head-on impact, the galaxies are likely to experience a glancing first encounter, with Andromeda sliding past the Milky Way before gravity pulls them back together for additional passes. This cosmic dance will unfold over hundreds of millions of years before the two galaxies finally merge into a single, larger galaxy. As we contemplate Andromeda's approach, it's natural to wonder about the consequences for Earth and our solar system. The vast distances between stars make direct stellar collisions extremely unlikely, even when galaxies merge. Our solar system will probably maintain its integrity throughout the merger, though it may be thrown into a different orbit around the new galaxy's center. However, by the time the collision begins, Earth may already be uninhabitable due to the Sun's increasing luminosity as it ages. The discovery of Andromeda as a separate galaxy not only expanded our cosmic horizon, but also raised profound questions about the origin and evolution of galaxies. How did these vast stellar systems form? How have they changed over cosmic time? And what does their future hold? The Andromeda Galaxy, as our nearest large galactic neighbor, provides a unique laboratory for exploring these questions. Observations of Andromeda and other nearby galaxies have revealed that most large galaxies have grown through mergers, with smaller galaxies a process of cosmic consolidation that continues today. The stellar halos surrounding both the Milky Way and Andromeda contain the remains of smaller galaxies consumed throughout their histories. The approaching collision between these giants represents the inevitable continuation of this process. Beyond its scientific significance, Andromeda has captured the human imagination as a symbol of cosmic vastness and possibility. Visible to the naked eye despite its enormous distance, it serves as a tangible reminder that our Milky Way is not alone in the universe. For the ancient Persian astronomers who first noted its presence, for Edwin Hubble who discerned its true nature, and for backyard stargazers today who seek out its faint glow, Andromeda represents a window onto the greater cosmos. Modern technology has allowed us to study Andromeda in unprecedented detail across the electromagnetic spectrum. Radio telescopes map its hydrogen gas, revealing the raw material from which new stars form. Infrared observatories penetrate its dust clouds to expose hidden star formation. Ultraviolet telescopes highlight its youngest, hottest stars. X-ray observatories detect the high-energy radiation from its central regions and stellar remnants. Each wavelength reveals a different aspect of this complex and beautiful galaxy. These multi-wavelength observations have allowed astronomers to reconstruct Andromeda's history and predict its future. We now know that Andromeda formed more than 10 billion years ago from the merger of smaller proto-galaxies in the early universe. It has continued to grow by absorbing dwarf galaxies, including a significant merger approximately 2 billion years ago that triggered a burst of star formation throughout its disk. And its future includes the most significant merger yet with our own Milky Way. As astronomical techniques continue to improve, our understanding of Andromeda grows ever more sophisticated. Adaptive optic systems on ground-based telescopes now correct for atmospheric distortion, providing images almost as sharp as those from space telescopes. Interferometry combines the light from multiple telescopes to achieve even higher resolution. And planned facilities, like the James Webb Space Telescope, promise to reveal Andromeda in even greater detail. From a faint little cloud, noted by ancient astronomers, to a vast spiral galaxy, whose collision course with our own has been precisely calculated, Andromeda represents one of humanity's greatest journeys of discovery. This luminous spiral, visible on clear nights, even without optical aid, connects us to both our scientific heritage and our cosmic future. When we gaze at Andromeda, we look not only across space but across time to the distant past, when its light began its journey to Earth, and to the future, when its stars will mingle with our own. We once looked at Andromeda as a distant light. Now we know it's headed our way. Despite this evolution toward greater emptiness, the connection between the two galaxies has strengthened. As the universe expands, it carries most galaxies away from each other. But within the local group, gravity overcomes this expansion, binding galaxies together in a gradually contracting system. The Milky Way and Andromeda, as the local group's largest members, dominate this gravitational dance, pulling each other closer across the intergalactic void. The motion of Andromeda relative to the Milky Way reveals the influence of the matter both visible and dark that fills the space between them. Andromeda moves toward our galaxy at approximately 110 kilometers per second, a velocity determined by the gravitational attraction between the two galaxies and modified by the distribution of mass throughout the local group. This approaching motion will, over billions of years, traverse the vast gulf that currently separates the two galaxies. Intergalactic space serves not only as a medium through which galaxies move, but as a repository for material ejected from galaxies. The space between the Milky Way and Andromeda contains elements forged in the stars of both galaxies and expelled through stellar winds, supernovae, or galactic outflows powered by star formation or active galactic nuclei. This expelled material enriches the intergalactic medium, potentially becoming the raw material for future generations of stars when it eventually accretes onto galaxies. The exchange of material between galaxies and intergalactic space represents a cosmic recycling process essential to galactic evolution. Galaxies expel gas into intergalactic space, enriching it with heavy elements. This enriched material eventually flows back into the same or different galaxies, influencing the composition of new stars and planets. The space between galaxies thus serves as both a destination for galactic outflows and a source of material for future galactic growth. As the Milky Way and Andromeda move toward each other, they plow through the intergalactic medium, potentially creating bow shocks similar to those produced by spacecraft entering planetary atmospheres, but on a vastly larger scale. These shocks compress and heat the intergalactic gas, potentially making it detectable through its X-ray emission. However, the extreme rarefaction of this gas makes such effects subtle and difficult to observe from our position within the Milky Way. The journey of light across intergalactic space reveals important properties of the cosmic void. As photons travel from Andromeda to Earth, they occasionally interact with the intervening matter, providing astronomers with information about the composition and state of the intergalactic medium. Absorption lines in the spectra of distant galaxies and quasars reveal the presence of various elements and compounds in intergalactic space, while the precise wavelengths of these lines indicate the motion of the absorbing material. One of the most powerful tools for studying intergalactic space is the Lyman Alpha Foresta series of absorption lines in the spectra of distant light sources produced by neutral hydrogen along the line of sight. By analyzing these absorption features, astronomers can map the distribution of hydrogen across vast distances and trace the cosmic web of filaments and voids. This technique has revealed that matter in the universe is organized in a complex network of interconnected structures, with galaxies forming at the nodes where filaments intersect. The space between galaxies also contains the imprint of cosmic expansion. As the universe expands, it carries most galaxies away from each other, stretching the intergalactic void. This expansion leaves its mark on the cosmic microwave background radiation, the distribution of galaxies, and the absorption patterns in the light from distant sources. By measuring these effects, astronomers can determine the rate of cosmic expansion and infer the presence and properties of dark energy, the mysterious force that accelerates this expansion. At the largest scales, intergalactic space is not uniform, but structured into a cosmic web of filaments surrounding vast voids. Galaxies tend to cluster along these filaments, forming groups and clusters at the intersections. The local group, including the Milky Way and Andromeda, resides in one such filament, part of the larger Virgo supercluster. This position within the cosmic web influences the flow of matter between galaxies and the evolution of the local group as a whole. As we contemplate the vast gulf between our galaxy and Andromeda, we gain perspective on cosmic distances and connections. The space between galaxies, far from being an empty void, is a dynamic medium through which matter, energy, and information flow. It connects galaxies through gravity, magnetic fields, and the exchange of material. And it provides the stage upon which the cosmic drama of galactic evolution and interaction unfolds. The Milky Way and Andromeda, separated by millions of light years, remain bound together by the invisible threads of gravity. Across this seemingly empty space, the two galaxies pull each other closer, moving at 110 kilometers every second toward an encounter that will transform them both. What separates us is not space, it is time. And with each passing moment, that separation diminishes, bringing us closer to the moment when two become one. The merger of the Milky Way and Andromeda represents not only a dramatic event in our galaxy's future, but also a window into cosmic evolution on the largest scales. Galaxy mergers have been common throughout the universe's history and have played crucial roles in shaping the galaxies we observe today. The Milky Way itself has absorbed numerous smaller galaxies throughout its history, and its current interaction with the Sagittarius Dwarf's spheroidal galaxy offers a small-scale preview of the processes that will operate during the much larger collision with Andromeda. By studying this impending merger, astronomers gain insight into the fundamental processes that drive galactic evolution: the conversion of gas into stars, the redistribution of matter through gravitational interactions, the role of supermassive black holes in galactic nuclei, and the transformation of galactic morphology through cosmic time. The collision of the Milky Way and Andromeda, while dramatic from our perspective, represents just one event in an ongoing process of cosmic assembly and transformation that has operated since the first galaxies formed. This perspective reminds us that galaxies, like the stars and planets they contain, follow life cycles of formation, evolution, and transformation. The Milky Way and Andromeda, both products of previous mergers with smaller galaxies, will themselves become components of a larger system. This cycle of merging and growth reflects the hierarchical nature of structure formation in our universe, where small systems combine to form larger ones under the influence of gravity. As we contemplate the approaching collision between our galaxy and its nearest large neighbor, we gain perspective on cosmic timescales and the transient nature of even the largest structures in our universe. The familiar appearance of the Milky Way as a band of light across our night sky, essentially unchanged throughout human history, represents just a moment in the galaxy's long evolution. In the distant future, observers on Earth, if humanity or its descendants still exist, will witness a transformed sky, reflecting the ongoing drama of galactic evolution. The collision between the Milky Way and Andromeda, unfolding over billions of years, reminds us of the dynamic nature of our cosmos. Far from being static and eternal, the structures we observe are in constant motion and evolution, their current forms representing mere snapshots in cosmic time. Even something as vast as a galaxy, containing hundreds of billions of stars, eventually transforms through interaction with its cosmic environment. It will not be a crash. It will be a blending, reshaping of the sky. In considering the fate of Earth during this cosmic collision, we gain perspective on the different timescales that govern our universe. Human civilization has existed for only a few thousand years, a blink in cosmic time. The Milky Way-Andromeda merger will unfold over billions of years, a process so gradual that even geologically significant periods on Earth would reveal little noticeable change in the positions of the galaxies. This contrast between human timescales and cosmic ones reminds us of our brief presence in an extraordinarily long and complex cosmic story. This perspective also raises intriguing questions about potential observers of this spectacular event. While humanity in its current form will almost certainly not exist 4 billion years from now, it's conceivable that some form of intelligent life, perhaps descended from humanity, perhaps not, might witness the approaching collision. Would such observers understand what they were seeing? Would they have the knowledge to predict the merger's progression and ultimate outcome? Would they document the changing night sky for whatever form of posterity exists in that distant future? If technological civilization survives in some form, future astronomers might not be limited to Earth as an observation platform. Observatories throughout the solar system, or even in interstellar space, could provide multiple perspectives on the merger as it unfolds. Intelligent machines, possibly incorporating some form of human consciousness, might record the cosmic spectacle over timescales far exceeding current human lifespans, The galactic collision, while tremendously slow by human standards, might be experienced and documented by intelligences operating on different timescales, or with different perceptual capabilities than our own. For any such observers, the collision would provide a unique opportunity to study galaxy evolution up close. Most of our current understanding of galaxy mergers comes from observing distant systems caught at specific moments in their interaction. The Milky Way-Andromeda merger would offer future astronomers the chance to observe a collision from inside, documenting each stage as it unfolds over millions of years. The knowledge gained could revolutionize future understanding of galactic dynamics, star formation, and the evolution of cosmic structures. Regardless of whether intelligent observers witness the merger, Earth itself, or whatever remains of it, after the Sun's red giant phase will continue its journey through the cosmos, now as part of a larger, combined galaxy. If Earth somehow survives the Sun's expansion, perhaps through technological intervention by future civilizations, it would ultimately witness the birth of a new galactic structure and orbit within a cosmic environment fundamentally different from the one in which it formed. This new environment would differ from our current Milky Way in several significant ways. The merged galaxy, likely elliptical rather than spiral in shape, would contain fewer regions of active star formation. The interstellar medium would be more depleted, having been converted to stars during the starburst phase of the merger, or heated and expelled from the galaxy. The stellar population would be older on average, dominated by the lower mass stars that outlive their more massive counterparts. And the night sky would show a more uniform distribution of stars, rather than the concentrated band of the Milky Way. Another fascinating possibility concerns the appearance of other galaxies from Earth after the merger. Currently, our view of distant galaxies is partly obscured by dust in the Milky Way's disk, particularly when looking through the plane of our galaxy. In the merged elliptical galaxy, with its more diffuse distribution of stars and gas, observers on Earth might have clearer views of the distant universe. The cosmic horizon would expand, revealing galaxies currently hidden behind our own galaxy's dust. The fate of Earth during the Milky Way-Andromeda collision reminds us of our planet's place in the larger cosmic context. Earth exists within nested hierarchies of structure-a planet, orbiting a star, which orbits within a galaxy, which moves through a group of galaxies, which is part of a larger supercluster. Each level of this hierarchy evolves according to its own physics and timescales. The collision of galaxies, while enormous in scale and consequence for stellar systems, represents just one process in this multi-level cosmic evolution. This perspective also highlights the resilience of planetary systems within the larger cosmic dance. Despite the tremendous energies and forces involved in a galactic collision, individual planetary systems like our own are likely to survive intact, their internal dynamics governed more by their parent star's gravity than by the larger galactic transformation. Earth has orbited the Sun for 4.5 billion years, as the solar system has completed about 20 circuits around the Milky Way. It may continue to orbit the Sun, or whatever remains of Etas, the very galaxy in which it resides, transforms around it. The unlikely survival of Earth through this galactic metamorphosis serves as a reminder of the vastness of space relative to the objects it contains. From the distance between atoms, to the gaps between stars, to the voids between galaxies, empty space dominates our universe. This predominance of emptiness, while sometimes giving an impression of cosmic loneliness, also provides a kind of buffer that allows structures to evolve and persevere even amidst the most dramatic cosmic events. If eyes still gaze upward, they will see a new world forming. To understand the journey between galaxies, we must first understand our place within our own cosmic home, the Milky Way. The name itself evokes images of luminous clouds stretching across the night sky, a river of stars flowing through the darkness. But what exactly is this galaxy we call home? Imagine floating away from Earth, rising above our planet, beyond our moon, past Mars and Jupiter and Saturn, until our Sun becomes just one point of light among many. Keep going, and soon the Sun vanishes entirely among hundreds of billions of other stars. This vast collection of stars, gas, dust, and unseen dark matter is our galaxy, Milky Way. If we could see it from outside, as we see Andromeda through our telescopes, the Milky Way would appear as a magnificent spiral. Not a perfect circle, but a flattened disk with elegant arms sweeping outward from a bright central bulge, like cosmic waves frozen in space. These spiral arms are not solid structures, but regions where stars and gas are more densely packed, areas where new stars are born at higher rates. Our galaxy measures approximately 100,000 light-years across. 1 light-year equals 9.5 trillion kilometers. To put this in perspective, if the entire Milky Way were reduced to the size of Earth, our solar system would be smaller than a grain of sand. And yet, this galaxy is our home, the only collection of stars humanity has ever known. The Milky Way has 4 main components, each telling us something about its history and evolution. First is the disk, a flattened region about 1,000 light-years thick, where most of the stars, including our Sun, orbit. The disk contains most of the galaxy's gas and dust, the raw materials from which new stars form. When you look at the band of the Milky Way stretching across the night sky, you are looking through this disk, edge on. Second is the central, bulgier, densely packed spherical collection of stars at the galaxy's heart. At the very center lies a supermassive black hole, 4 million times more massive than our Sun. Don't worry, though at 26,000 light-years away, it poses no threat to Earth. The stars in the bulge are generally older than those in the disk. Many formed when the galaxy was young. Third is the halo, a sparse, spherical region surrounding the entire galaxy. The halo contains the oldest stars in the Milky Way, some nearly as old as the universe itself. These ancient stars orbit the galaxy in all directions, not confined to the disk like our Sun. They are the living fossils of our galaxy, telling astronomers about conditions in the very early universe. Finally, there are the spiral arms, the characteristic features that give our galaxy its elegant structure. The Milky Way has several major arms, winding outward from the central regions. Our Sun resides in a smaller arm called the Orion Spur, nestled between the larger Perseus arm and Sagittarius arm. So where exactly are we in this vast cosmic structure? Our solar system sits about 26,000 light-years from the galactic center, roughly halfway between the center and the edge of the visible disk. We're in what astronomers call the galactic habitable zone, not too close to the dangerous radiation of the core, and not so far out that heavy elements necessary for planets and life are scarce. Our Sun, along with the planets, moons, asteroids, and comets that orbit it, is moving through space in several ways simultaneously. Earth orbits the Sun orbits the center of the Milky Way, and the Milky Way itself moves through the cosmos. Let's focus on our galactic motion. Our solar system travels through the Milky Way at approximately 220 kilometers per second. At this speed, we complete one orbit around the galactic center approximately every 230 million years. This means that since the time of the dinosaurs, our solar system has completed less than 1/3 of a single galactic orbit. And since modern humans evolved, we've traveled only about 1/7,000th of the way around the galaxy. This period of one full orbit around the galaxy is sometimes called a cosmic year. During a single cosmic year, the entire solar system travels a distance of approximately 150,000 light-years, a cosmic journey that would take light itself 150 millennia to complete. And yet, despite this enormous distance, our Sun has completed only about 20 to 25 orbits since it formed 4.6 billion years ago. As we travel through the galaxy, we don't simply follow the spiral arms. Our Sun actually passes through them. The spiral arms themselves are more like cosmic traffic jams regions, where stars, gas, and dust temporarily bunch up as they orbit the galaxy at different speeds. Our solar system passes through these denser regions every few tens of millions of years, which may have consequences for Earth. Some scientists speculate that these passages might trigger periods of increased comet activity, potentially affecting Earth's climate or even causing mass extinctions. Looking up at night, we see only the tiniest fraction of our galaxy. On the clearest night, far from city lights, the naked eye can detect perhaps a few thousand stars, all of them relatively close neighbors in our small corner of the Milky Way. The entire band of the Milky Way that stretches across our sky is composed of millions of stars too distant and numerous to distinguish individually, blending together into that familiar glowing river. Our view of the galaxy is limited not only by the power of our eyes, but by cosmic dust. Dense clouds of interstellar dust block visible light, particularly toward the galactic center. This is why we cannot see the core of our own galaxy with the naked eye, though it would be the brightest feature in our night sky if this dust were not in the way. In a sense, we live in a cosmic haze, with our view of much of our own galactic home obscured. For most of human history, we did not know we lived in a galaxy at all. The true nature of the Milky Way was discovered only in the early 20th century, when astronomer Harlow Shapley mapped the distribution of globular cluster-spherical collections of stars that orbit the Milky Way and determined the Sun's position relative to the galaxy's center. Before that, some astronomers thought the visible Milky Way constituted the entire universe. Life beneath the spinning stars of the Milky Way has evolved in harmony with our galactic environment. The heavy elements in our body's carbon, oxygen, nitrogen, iron were forged in the hearts of stars that lived and died before our Sun formed. When massive stars reached the end of their lives and exploded as supernovas, they scattered these elements across the galaxy. Eventually, some of this star stuff gathered into our solar system, our planet, and eventually into us. In a very real sense, we are children of the Milky Way. Our bodies contain atoms that have traveled thousands of light years, that have been part of countless stars before becoming part of us. The iron in our blood, the calcium in our bones, the oxygen we breathe whole were created in stellar furnaces scattered throughout our galaxy. And yet, despite this intimate connection, we are only beginning to understand our galactic home. Modern telescopes, particularly those that detect radio waves, infrared light, and X-rays that penetrate the obscuring dust, are revealing the Milky Way's structure in unprecedented detail. Space missions like Gaia are mapping the positions and motions of billions of stars, creating the most detailed three-dimensional map of our galaxy ever attempted. What these studies reveal is that our galaxy is not an isolated island in space. It is part of a larger cosmic ecosystem, interacting with neighboring galaxies through gravity, and occasionally merging with smaller galaxies that stray too close. In fact, the Milky Way's history is one of growth through such mergers, absorbing smaller galaxies throughout its lifetime. Even now, it is in the process of consuming several dwarf galaxies, including the Sagittarius dwarf spheroidal galaxy, whose stars are being slowly incorporated into the Milky Way's disk and halo. But these past and ongoing mergers pale in comparison to what awaits in our galaxy's future. For the Milky Way is on a collision course with a galaxy of comparable size Andromeda, and unlike the smaller galaxies the Milky Way has consumed, this encounter will fundamentally transform both galaxies. We orbit in a spiral, but that spiral is not still. Our galaxy moves through space at hundreds of kilometers per second, carried by invisible currents of gravity. And it is these same currents that draw Andromeda closer with every passing moment. The quiet revolution of our solar system around the galactic core creates another fascinating phenomenon: cosmic neighborhoods. Just as your town or city has different neighborhoods with unique characteristics, our galaxy contains regions with varying stellar populations, gas densities, and radiation levels. Currently, our solar system travels through what astronomers call the local bubble, a vast, relatively empty region spanning about 500 light-years, created by ancient supernova explosions that blew away much of the gas and dust. This cosmic clearing affects our night sky, our planet's exposure to cosmic rays, and potentially even our climate. In about 30,000 years, our solar system will enter a different region, a nearby interstellar cloud with higher densities of gas and dust. This transition could alter the heliosphere, the protective bubble created by our sun's solar wind that shields our planets from cosmic radiation. Such transitions, occurring roughly every few 100,000 years, mark the changing cosmic seasons of our galactic journey. To visualize the scale of our galaxy, imagine the Milky Way reduced to the size of North America. At this scale, our solar system would be smaller than a coffee cup, and our entire orbit around the galaxy would be a circle roughly the diameter of the continent. Each star would be separated from its neighbors by hundreds of kilometers. Yet within this enormous structure, gravity binds everything together in a cosmic ballet of breathtaking precision. Our position in the Milky Way's Orion Spur offers us a unique perspective on the cosmos. From our vantage point, we can observe both the dense star fields toward the galactic center and the sparser regions toward the outer rim. When we look up at the band of the Milky Way, we are seeing our galaxy edge on, gazing through thousands of light years of stars, gas, and dust. This perspective has shaped human culture since our earliest days. The Milky Way features prominently in mythologies around the world, seen as a river in the sky by Chinese astronomers, as spilled milk by ancient Greeks, as the backbone of the night by the Kalahari Bushmen, and as the pathway of souls by the Iroquois. These diverse interpretations share a common recognition of our galaxy's majesty and mystery. The rotation of our galaxy creates another phenomenon that affects our view of the cosmos, what astronomers call differential rotation. The Milky Way does not rotate like a solid wheel. Instead, stars closer to the center complete their orbits more quickly than those farther out, just as planets closer to the Sun orbit more quickly than distant ones. This means that over millions of years, the patterns of stars we see gradually distort as nearer stars overtake more distant ones in their galactic journeys. The constellations familiar to us today, Orion, Ursa Major, Cassiopeia, merely temporary arrangements, snapshots in cosmic time. If we could fast forward 1 million years, these patterns would be unrecognizable, transformed by the galaxy's rotation. The Big Dipper would no longer resemble a ladle, and Orion would have lost his distinctive belt and sword. As our solar system orbits the galactic center, it also moves up and down through the galactic disk in a wave-like motion, completing one full vertical oscillation every 60 million years or so. At times, we travel above the galactic plane, at others, below it. Currently, we are about 20 light-years above the precise midplane of the galaxy, moving upward at about 7 kilometers per second. These vertical oscillations may influence Earth's history in profound ways. When our solar system crosses the densest part of the galactic plane, we encounter higher concentrations of interstellar matter and potentially stronger gravitational disturbances. Some researchers have suggested these crossings might correlate with mass extinction events on Earth by disturbing the Oort Cloud, a vast shell of icy objects surrounding our solar system and sending comets toward the inner planets. Our journey through the Milky Way is not perfectly circular either. The combined gravitational influence of billions of stars, plus vast clouds of dark matter-invisible material that reveals itself only through its gravitational effects, gives our orbit a slight elliptical shape. Sometimes we drift closer to the galactic center, at other times, farther away, though these variations are relatively small compared to the overall radius of our orbit. The structure of our galaxy influences not just the motions of stars, but the very process of star formation itself. The spiral arms are not merely decorative features. They are dynamic regions where interstellar gas is compressed, triggering the birth of new stars. As our solar system passes through these arms every few tens of millions of years, we witness, from a safe distance, spectacular stellar nurseries where new suns ignite. When we observe these star-forming regions through telescopes, we see clouds of gas and dust illuminated by the hot, young stars recently born within them. The famous Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one such stellar nursery relatively close to Earth, just 1,400 light-years away. Similar, but far larger star-forming regions exist throughout the spiral arms of our galaxy. Our Sun, however, is a quieter resident of the Milky Way. At 4.6 billion years old, it is a middle-aged star, having completed roughly half its expected lifetime. It formed from the collapsed remnants of previous stellar generations, inheriting their elemental legacy. This stellar recycling is visible in our Sun's composition: roughly 73% hydrogen, 25% helium, and 2% heavier elements, the ash of ancient stars that lived and died before our Sun existed. The presence of these heavier elements, what astronomers call metals, though they include non-metallic elements like carbon and oxygen, made possible the formation of rocky planets like Earth. The first generation of stars in our galaxy contained only hydrogen and helium. Only after these stars produced heavier elements and scattered them through space could planets like ours form. In this sense, the Earth itself is evidence of our galaxy's age and evolutionary history. As we continue our orbital journey around the galactic center, we are not alone. The solar system is surrounded by other stars, many with their own planets. The closest, Proxima Centauri, lies just 4.2 light-years away, a distance that would take our fastest spacecraft tens of thousands of years to traverse. Beyond it lies the Alpha Centauri binary system, and beyond that, countless other stars, each moving on its own orbit through the galaxy. Over time, these stellar neighbors change. Stars that were close to our solar system millions of years ago have since moved away, while others have drawn nearer. In about 1.3 million years, a star called Gliese 710 will pass within just 1 light-year of our Sun, closer than any star has come during humanity's existence. These changing stellar neighborhoods are another reminder of the dynamic nature of our galaxy. Despite the vastness of the Milky Way and the seemingly immense distances between stars, our galaxy is actually quite crowded when viewed on cosmic scales. If the Milky Way were a city, the average distance between neighboring stars would be comparable to the distance between houses in a suburban neighborhood. Close enough for gravitational interaction, yet far enough apart that direct collisions are exceedingly rare. This delicate balance of proximity and distance characterizes life in the galactic disk. Stars influence each other through gravity, occasionally altering orbits or even ejecting companions into intergalactic space. Yet they rarely collide, allowing for stable planetary systems where life might evolve undisturbed for billions of years, as it has on Earth. Our place in the galaxy has provided a stable cosmic environment for life to flourish, far enough from the energetic center to avoid its hazards, yet close enough to contain the heavy elements needed for rocky planets and biological chemistry. In the Goldilocks zone of our galaxy, not too hot, not too cold, Earth has been a haven for life for nearly 4 billion years. But this stable environment is not permanent. Just as our planet changes over geological time, our galaxy evolves over cosmic time. Stars burn through their fuel and die. New stars form from the recycled material. And galaxies, drawn by gravity, move inexorably through space, sometimes away from each other, carried by the expanding universe, but sometimes, fatefully, toward each other. We orbit in a spiral, but that spiral is not still. It moves, breathes, evolves, and it is on a collision course with our largest galactic neighbor. The Andromeda Galaxy, visible to the naked eye as a faint smudge in the constellation that bears its name, is heading straight for us. When we gaze at the night sky, the stars appear fixed, unchanging sentinels in the darkness. Even the planets, whose very name means wanderer in ancient Greek, seem to move slowly against the backdrop of stars. This apparent stillness is an illusion, a product of human timescales. In reality, everything in the cosmos is in perpetual motion. Stars orbit galaxy centers. Galaxies move through space. The universe itself expands in all directions. Tonight, we explore this cosmic choreography and discover how it shapes the destiny of our galactic home. The Milky Way, like all galaxies, is not fixed in space. It travels through the cosmos at approximately 630 kilometers per second. This speed, nearly 1,400 miles per hour, means that in the time it takes you to read this sentence, our entire galaxy has moved thousands of kilometers through space. And yet, we feel nothing of this motion. No cosmic wind rushes past. No stellar turbulence disturbs our solar system. The movement happens in the vast silence of space, where distance dampens all sensation. This galactic motion has several components. First, the Milky Way orbits within a structure called the Local Group, a collection of more than 50 galaxies bound together by gravity. The local group spans roughly 10 million light-years and contains two dominant member solar, Milky Way and the Andromeda Galaxy, along with numerous smaller galaxies. These smaller neighbors include the Triangulum Galaxy, the Large and Small Magellanic Clouds, and dozens of dwarf galaxies, some orbiting the Milky Way like satellites around a planet. Within this local group, the Milky Way and Andromeda reign as twin giants, each containing hundreds of billions of stars. They orbit a common center of mass, drawn together by their mutual gravitational attraction. This attraction overcomes even the expansion of the universe, which would otherwise drive them apart. In the language of cosmology, they are gravitationally bound. Their fate to encounter one another, inevitable. But the local group itself is not stationary. It moves through space as part of an even larger structure, the Virgo supercluster. This immense cosmic neighborhood contains over 100 galaxy groups and clusters, spanning more than 110 million light-years. The combined gravitational pull of this enormous assemblage influences the motion of every galaxy within it, including our own. And even the Virgo supercluster is being pulled towards something greater, a massive concentration of galaxies called the Great Attractor. This gravitational behemoth, located approximately 150 million light-years from Earth, influences the motion of thousands of galaxies across hundreds of millions of light-years of space. Beyond the Great Attractor lies the Shapley supercluster, pulling everything in our cosmic neighborhood toward its enormous mass. Recent astronomical surveys have revealed that these structures are part of an even grander cosmic architecture. The Virgo supercluster is now understood to be just one lobe of a larger structure called the Laniakea supercluster, a name derived from Hawaiian words meaning immense heaven. Laniakea spans more than 500 million light-years and contains approximately 100,000 galaxies. Our Milky Way resides in the outskirts of this enormous cosmic structure, its motion dictated by the combined gravitational influence of countless galaxies, spread across hundreds of millions of light-years. This nested hierarchy of cosmic structures, from galaxy to group to cluster to supercluster, creates a complex web of gravitational interactions. Like water flowing through a river system, galaxies move along cosmic currents defined by the distribution of matter throughout space. Some regions, dense with galaxies and dark matter, act as gravitational sinks, drawing in surrounding material. Other regions, relatively empty, form cosmic voids where few galaxies venture. Astronomers call this vast network of galactic clusters, filaments, and voids the cosmic web. It resembles a three-dimensional spider's web, with galaxies concentrated along filaments that connect to dense nodes, surrounding vast bubble-like voids. This is the largest known structure in the universe, and it shapes the motion of every galaxy, including our own. The Milky Way's journey through this cosmic web is influenced not only by the visible matter we can observe, stars, gas, and dust, but also by dark matter, an invisible substance that reveals itself only through its gravitational effects. Dark matter makes up approximately 85% of all matter in the universe, forming an unseen scaffold that guides the formation and evolution of cosmic structures. This dark matter forms a vast halo around our galaxy, extending far beyond the visible disk. The Milky Way sits within this halo like a ship in an invisible ocean, its motion determined as much by the unseen currents of dark matter as by the gravitational pull of neighboring galaxies. Similar halos surround Andromeda and every other galaxy, creating a complex gravitational landscape through which galaxies navigate. The motion of galaxies leaves traces that astronomers can detect. As galaxies interact gravitationally, they sometimes strip material from one another, creating long, tenuous streams of stars and gas that trail behind them like cosmic contrails. The Milky Way displays several such features, including the Sagittarius streamer ribbon of stars torn from the Sagittarius dwarf galaxy as it orbits and gradually merges with our galaxy. These stellar streams are like cosmic fossils, preserving the history of galactic interactions over billions of years. By studying their properties, astronomers can reconstruct past encounters between galaxies and predict future ones. They tell us that the Milky Way has consumed several smaller galaxies throughout its history, growing larger with each galactic meal. The motion of galaxies also reveals itself in another, more subtle way through the redshift or blueshift of their light. Just as the pitch of an ambulance siren changes as it passes by, the wavelength of light from a moving galaxy shifts depending on whether it is moving toward or away from us. Galaxies moving away appear redder than they actually are. those moving toward us appear bluer. By measuring these shifts, astronomers can determine precisely how fast and in which direction galaxies are moving. Most galaxies in the universe exhibit redshift, meaning they are moving away from use evidence of the universe's expansion. But some nearby galaxies, bound to us by gravity, show blue shift. The most significant of these is Andromeda, approaching us at approximately 110 kilometers per second. This approaching motion will, eventually, bring Andromeda and the Milky Way together. But space is vast, and even at this speed fast enough to circle Earth in 6 minutes, the journey will take billions of years. The two galaxies, currently separated by 2.5 million light-years, will not begin their cosmic dance for another 4 billion years. When galaxies move through space, they do not travel alone. They carry with them vast entourages of satellite galaxies, globular clusters, and streams of stars torn from past galactic encounters. The Milky Way travels with more than 50 known satellite galaxies, the largest being the Large Magellanic Cloud, visible from the southern hemisphere as a fuzzy patch in the night sky. These satellite galaxies orbit the Milky Way like moths around a flame, their paths dictated by our galaxy's gravitational field. Some will eventually spiral inward and merge with the Milky Way, contributing their stars to our galaxy's disk and halo. Others may be torn apart by gravitational tides, forming new stellar streams. A few might escape our galaxy's gravitational pull entirely, flung into intergalactic space by gravitational interactions with other satellites. Andromeda possesses its own system of satellite galaxies, including the prominent Triangulum Galaxy, also known as Messier 33. When the Milky Way and Andromeda eventually meet, these satellite systems will interact in complex ways. Some satellites may be captured by the other galaxy, others might be ejected from the local group entirely. Many will participate in the merger, their stars becoming part of the new galaxy that will form from the collision. The motion of galaxies is not always smooth and orderly. Sometimes, galaxies experience sudden accelerations, cosmic kicks, that alter their trajectories. These kicks can result from gravitational interactions with other galaxies, or from asymmetric outflows of material, such as when a supermassive black hole at a galaxy's center ejects material in a particular direction, generating a rocket-like thrust in the opposite direction. Some galaxies in our universe travel at extraordinary speeds, over 3,000 kilometers per second, having been accelerated by gravitational slingshot effects or powerful galactic outflows. These hypervelocity galaxies race through the cosmos, some potentially fast enough to escape the gravitational pull of the entire visible universe. The Milky Way, by comparison, moves at a more stately pace. On a clear autumn night in the northern hemisphere, far from city lights, a faint smudge of light is visible to the naked eye in the constellation Andromeda. This hazy patch, easily overlooked by casual stargazers, represents one of the most significant objects in our cosmic neighborhood, the Andromeda Galaxy. Today, we know this luminous spiral as our galaxy's largest neighbor, a vast island of stars more than 2.5 million light-years from Earth. But the recognition of Andromeda's true nature represents one of the greatest leaps in our understanding of the universe. The story of humanity's discovery of Andromeda begins more than 1,000 years ago. The Persian astronomer Abd al-Rahman al-Sufi first documented this celestial object around 964 CE in his Book of Fixed Stars, describing it as a little cloud. For centuries after, it remained just that a curious, nebulous patch among the stars, its true significance unrecognized. European astronomers rediscovered this nebula in the 17th century. German astronomer Simon Marius described it in 1612 as resembling the flame of a candle seen through horn. Charles Messier, the famous French comet hunter, catalogued it in 1774 as Messier 31, the 31st entry in his famous list of objects to avoid when searching for comets. None of these early observers imagined they were looking at another galaxy entirely. The mystery of the Andromeda Nebula, as it was then known, deepened in the 19th century. In 1864, William Huggins used spectroscopy to study its light, and found that, unlike gaseous nebulae, Andromeda's spectrum resembled that of individual stars. This suggested it was not a cloud of gas, but a vast collection of stars, too distant to resolve individually. But was this collection within our own galaxy, or beyond it? The answer to this question would fundamentally change our understanding of the cosmos. Throughout the late 19th and early 20th centuries, astronomers debated the nature of the spiral nebulae, like Andromeda. Some believed these objects were relatively nearby, forming within the Milky Way, which was thought to encompass the entire universe. Others proposed they might be distant island universes, separate galaxies like our own, scattered throughout a much larger cosmos. This debate reached its climax in 1920, when the great debate between astronomers Harlow Shapley and Heber Curtis took place at the National Academy of Sciences in Washington, D.C. Shapley argued that the spiral nebulae were part of the Milky Way, while Curtis contended they were distant galaxies in their own right. The question remained unresolved until a breakthrough came from an unexpected source. Diligent astronomer, working with the world's largest telescope, Edwin Hubble, working at the Mount Wilson Observatory in California, made the decisive discovery. Using the 100-inch Hooker telescope, Hubble observed individual stars within the Andromeda Nebula, including Cepheid Variable special stars, whose brightness fluctuates in a predictable pattern that reveals their true luminosity. By measuring their apparent brightness and comparing it to their known intrinsic brightness, Hubble could calculate their distance. In 1924, Hubble announced his findings. Andromeda lay far beyond the boundaries of the Milky Way. His initial estimate placed it at about 900,000 light-years away, vast distance that firmly established Andromeda as a separate galaxy. Though this estimate was later revised to approximately 2.5 million light-years, the essential conclusion remained. The universe was immensely larger than previously thought, containing not just one galaxy, but countless others. This discovery fundamentally transformed our cosmic perspective. The Milky Way was demoted from the entire universe to just one galaxy among billions. The spiral nebulae were recognized as distant galaxies in their own right, and the cosmos expanded from a single island of stars to an archipelago stretching across unimaginable distances. Few scientific discoveries have so profoundly altered our place in the universe. With Andromeda's status as a separate galaxy confirmed, astronomers turned their attention to understanding its properties and relationship to our own galaxy. They discovered that Andromeda is a spiral galaxy, similar in structure to the Milky Way, with a flat disk, spiral arms, and a central bulge. Its spiral pattern is more tightly wound than our galaxies, giving it a somewhat different appearance when viewed face-on. As astronomical techniques improved, so did our understanding of Andromeda's size and mass. Modern measurements reveal that Andromeda spans approximately 220,000 light-years in diameter, more than twice the size of the Milky Way. It contains approximately 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion. This makes Andromeda the largest galaxy in the local group, by a considerable margin. The relationship between Andromeda and the Milky Way took an unexpected turn in the 1920s, when astronomer Vesto Slipher measured Andromeda's motion using the Doppler effect. While most galaxies show redshifts, indicating they are moving away from us, Andromeda shows a blue shift evidence that it is moving toward the Milky Way at approximately 110 kilometers per second. This discovery planted the first seed of an idea that would later blossom into our understanding of the galaxy's shared destiny. Throughout the 20th century, as telescopes grew more powerful and observational techniques more sophisticated, our portrait of Andromeda became increasingly detailed. Radio telescopes revealed vast reservoirs of hydrogen gas extending far beyond the visible disk. Infrared telescopes pierced the obscuring dust to reveal the galaxy's true structure. X-ray observatories detected the hot gas surrounding the galaxy and the radiation from its central regions. The Hubble Space Telescope, named for the astronomer who first determined Andromeda's true nature, has provided the most spectacular views of our galactic neighbor. Launched in 1990, Hubble has captured images of Andromeda with unprecedented clarity, resolving individual stars, star clusters, and nebulae within its spiral arms. One of Hubble's most impressive achievements was a panoramic image of a portion of Andromeda containing over 100 million stars, the largest and sharpest image ever taken of our neighboring galaxy. These observations have revealed striking similarities and differences between Andromeda and the Milky Way. Like our galaxy, Andromeda has a supermassive black hole at its center, estimated to be 100 to 200 million times the mass of our Sun, considerably larger than the Milky Way's central black hole. Both galaxies are surrounded by a swarm of satellite galaxies, though Andromeda's entourage is somewhat larger and more diverse. Perhaps the most significant difference between the galaxies lies in their recent star formation history. The Milky Way continues to form stars at a modest rate, particularly in its spiral arms. Andromeda, by contrast, experienced a significant burst of star formation approximately 2 billion years ago, possibly triggered by a collision with a smaller galaxy. Since then, its star formation rate has declined, giving the galaxy a somewhat redder overall appearance compared to the Milky Way. Andromeda's relationship with its satellite galaxies has provided valuable insights into galactic evolution. Its two largest satellites, known as M32 and M110, are visible even in small telescopes. M32 is particularly interesting, a compact elliptical galaxy that may once have been a larger spiral galaxy before Andromeda's gravitational pull stripped away its outer regions. This interaction offers a preview of the complex gravitational ballet that will occur when Andromeda and the Milky Way themselves begin to merge. Beyond these larger satellites, Andromeda hosts numerous dwarf galaxies, some discovered only in recent decades. These smaller systems orbit the main galaxy like moons around a planet, many gradually losing stars to Andromeda's gravitational pull. Streams of stars torn from these dwarfs create luminous trails that trace their orbits, revealing the ongoing process of galactic consumption that helps large galaxies like Andromeda grow over cosmic time. Astronomers have detected similar stellar streams around the Milky Way, suggesting that both giant spirals have grown by absorbing smaller galaxies throughout their histories. However, these past mergers involved relatively small galaxies. The impending collision between the Milky Way and Andromeda will be a meeting of near equals that will transform both galaxies fundamentally. The discovery that Andromeda is approaching the Milky Way led astronomers to investigate the future of our galactic neighborhood in detail. Initial calculations suggested the galaxies would collide in approximately 5 to 6 billion years. However, more precise measurements from the Hubble Space Telescope and the European Space Agency's Gaia mission have refined this timeline, indicating that the first close approach will occur in approximately 4.5 billion years, roughly around the time our Sun is expected to become a red giant. When we observe Andromeda through a telescope, we see more than just a distant collection of stars. We witness a complex cosmic structure with its own unique architecture, history, and character. Like examining the layout of an unfamiliar city from above, studying Andromeda's structure reveals patterns that tell stories of its formation, evolution, and future. Tonight, we explore the anatomy of our nearest large galactic neighbor, comparing and contrasting it with our own Milky Way. Andromeda, also catalogued as Messier 31 or NGC 224, presents itself to our telescopes tilted at an angle of approximately 77 degrees. This fortuitous orientation allows us to see both its spiral structure and its three-dimensional form. If we could view it perfectly face-on, we would see a magnificent spiral with two prominent arms winding outward from a bright central bulge. From directly edge-on, it would appear as a thin line with a central bulge, similar to how the Milky Way appears in our night sky. The most immediately striking feature of Andromeda is its sheer size. Its visible disk spans approximately 220,000 light-years from edge to edge, more than twice the diameter of the Milky Way. If Andromeda were placed where the Milky Way is, it would dominate our night sky, spanning an area several times larger than the full moon. The galaxy's enormous size reflects its greater mass and more extensive history of galactic mergers compared to our own galaxy. Like the Milky Way, Andromeda consists of several distinct structural components, each telling part of the galaxy's story. At its heart lies the central bulgier spherical region, approximately 15,000 light-years in diameter, densely packed with primarily older, redder stars. This bulge appears more prominent than the Milky Way's, suggesting differences in the two galaxies' formation histories. At the very center of this bulge sits a supermassive black hole, estimated at 100 to 200 million solar masses, substantially larger than our galaxy's central black hole. Surrounding the bulge is Andromeda's most distinctive feature, its spiral disk. This relatively flat region contains the majority of the galaxy's stars, organized into spiral arms that wind outward from the central regions. Unlike the Milky Way's somewhat patchy, loosely wound spiral structure, Andromeda's spiral pattern appears more tightly wound and less distinct when viewed through telescopes. The arms themselves consist of not just stars, but also gas, dust, star clusters, and nebulae, full ecosystem of a living galaxy. Andromeda's disk displays a remarkable feature not seen in the Milky Way, a series of concentric rings of star formation. These rings appear as circular ripples centered on the galaxy's nucleus, particularly visible in ultraviolet light that highlights young, hot stars. Astronomers believe these rings may have formed from a head-on collision with a smaller galaxy approximately 250 million years ago, which sent shockwaves outward through the disk, triggering waves of star formation like ripples in a cosmic pond. Another distinctive feature is Andromeda's dust lanes, dark streaks that trace the inner regions of the spiral arms, particularly visible when the galaxy is viewed through large telescopes. These lanes consist of interstellar dust that blocks light from stars behind them. By mapping these dust lanes, astronomers can trace the structure of the galaxy's spiral arms, even when the arms themselves are not distinctly visible in ordinary starlight. Beyond the visible disk lies Andromeda's extended diska region, detectable only through sensitive observations, that extends the galaxy's diameter to as much as 260,000 light-years. This tenuous region contains fewer stars than the main disk, but significant amounts of hydrogen gas, the raw material from which new stars form. Recent studies have detected star formation even in these outer regions, indicating that Andromeda continues to grow and evolve at its edges. Surrounding the entire visible galaxy is an enormous halo of stars extending as much as 500,000 light-years from the galaxy's center. This halo contains primarily older stars that orbit the galaxy in all directions, not confined to the relatively flat disk. Many of these stars belong to globular cluster-spherical collections of hundreds of thousands of stars that orbit Andromeda like tiny satellite galaxies. Astronomers have catalogued more than 450 globular clusters orbiting Andromeda, compared to about 150 known in the Milky Way. The stellar halo itself appears to have multiple components, representing different episodes in Andromeda's formation history. The inner halo likely formed along with the original galaxy, while the outer halo contains stars stripped from smaller galaxies that Andromeda has absorbed throughout its history. By studying the chemical composition and motion of these halo stars, astronomers can reconstruct Andromeda's complex history of galactic mergers. Extending even beyond the stellar halo is Andromeda's dark matter halo, an enormous, invisible component detectable only through its gravitational effects. This dark matter halo contains the majority of Andromeda's mass and extends more than 1 million light-years from the galaxy's center. The motions of Andromeda's stars and satellite galaxies reveal the presence and distribution of this dark matter, which forms the gravitational scaffold upon which the visible galaxy rests. Among the most fascinating components of Andromeda's structure are its satellite galaxies, smaller galaxies that orbit the main galaxy, bound by its gravitational pull. Andromeda hosts at least 27 known satellite galaxies, with more likely awaiting discovery. The two largest and most prominent, designated M32 and M110, are visible even in small telescopes, appearing as fuzzy patches near the main galaxy. These satellite galaxies tell complex stories of their own. M32, a compact elliptical galaxy positioned close to Andromeda's disk, may once have been a larger spiral galaxy before its outer regions were stripped away by Andromeda's gravitational pull. M110, a dwarf elliptical galaxy, shows evidence of recent star formation, unusual for its type. The remaining satellites include a diverse collection of dwarf galaxies, each interacting with Andromeda in ways that sculpt both their own structure and that of their massive host. Andromeda's satellite system appears more extensive and diverse than the Milky Way's, reflecting the larger galaxy's greater gravitational influence. However, both galaxies share a puzzling feature in their satellite distributions. they appear to be arranged in a relatively flat plane, rather than in the more spherical distribution that simple orbital models would predict. This plane of satellites remains a challenge to current theories of galaxy formation, and may provide important clues about how large galaxies and their satellites form and evolve. Between Andromeda's disk and its satellites flow streams of stars-long, tenuous ribbons that trace the orbits of disrupted dwarf galaxies. As smaller galaxies orbit Andromeda, its gravitational tides gradually tear them apart, stretching their stars into streams that can wrap multiple times around the main galaxy. These stellar streams form a complex network around Andromeda, recording the history of its interactions with smaller galaxies over billions of years. The giant stellar stream is the most prominent of these feature-share ribbon of stars, extending more than 400,000 light-years from Andromeda. Discovered in 2001, this stream contains the remains of a dwarf galaxy that passed close to Andromeda between 700 million and 2 billion years ago. By tracing the path of this stream, astronomers can reconstruct the orbit of the disrupted galaxy and predict its ultimate fate. Andromeda's structure reveals itself differently across the electromagnetic spectrum. In visible light, we see primarily the stars that compose the bulk of the galaxy's visible mass. In ultraviolet light, the galaxy's youngest, hottest stars stand out, tracing regions of recent star formation in the spiral arms and rings. Infrared observations penetrate the galaxy's dust, revealing stars and structures otherwise hidden from view. Radio telescopes detect the cold hydrogen gas that permeates the galaxy's disk and extends far beyond the visible stars. This gas represents the raw material from which future generations of stars will form. X-ray observations reveal the galaxy's most energetic components: its central black hole, supernova remnants, and the hot gas that fills the space between stars. Each wavelength adds another layer to our understanding of Andromeda's complex structure. One of the most striking aspects of Andromeda's structure emerges when we map the motion of its stars and gas. Unlike a solid object, a galaxy rotates differentially. Material closer to the center completes an orbit more quickly than material farther out. This differential rotation causes the spiral arms to wind up over time, yet the arms persist for billions of years. This apparent contradiction, known as the winding problem, is resolved by understanding spiral arms not as fixed structures, but as density waves that move through the galactic disk, temporarily concentrating stars and gas as they pass. Andromeda rotates with a pattern similar to our own galaxy, but with some important differences. Its rotation curvature graph, showing orbital speed versus distance from the center, remains relatively flat, far from the galaxy's center. This indicates that the gravitational pull at large distances from the center is stronger than would be expected from the visible matter alone, providing compelling evidence for the presence of dark matter in Andromeda's outer regions. Studies of Andromeda's rotation have revealed another intriguing feature. The galaxy appears to have two distinct disks, rotating in the same direction, but at different speeds. The second disk may result from a collision with a smaller galaxy that occurred billions of years ago, adding its stars to Andromeda but in a slightly different orbital plane. This second disk provides further evidence of Andromeda's complex merger history. The structure of Andromeda, like that of all galaxies, is not static, but evolves over cosmic time. Star formation gradually converts gas into stars, altering the galaxy's composition. Interactions with satellite galaxies disturb the disk, triggering bursts of star formation and reshaping the spiral arms. The central black hole periodically becomes active as it consumes matter, potentially influencing the surrounding galaxy through powerful outflows of energy. Perhaps the most significant change in Andromeda's recent history occurred approximately 2 billion years ago, when it experienced a major merger with another galaxy. This event, recorded in the ages and compositions of stars throughout the galaxy, triggered a significant burst of star formation that temporarily transformed Andromeda into a much more active galaxy. The effects of this merger continue to influence Andromeda's structure today, visible in its disturbed outer regions and the distribution of stars in its halo. Comparing Andromeda's structure with that of the Milky Way reveals both similarities and important differences. Both are large spiral galaxies with central bulges, disks, and halos. Both host supermassive black holes at their centers and are surrounded by systems of satellite galaxies. But Andromeda is larger, contains more stars, and shows evidence of a more active merger history. Its bulge is more prominent, its spiral structure more tightly wound, and its system of globular clusters more extensive. These differences provide valuable insights into the diverse evolutionary paths that galaxies can follow. The Milky Way appears to have experienced a relatively quiet recent history, with no major mergers for billions of years. Andromeda, by contrast, shows evidence of significant mergers within the past few billion years. These different histories are written in the galaxy's structures, visible to astronomers who know how to read these cosmic texts. Despite their differences, both galaxies share a common future. The structures we observe today, Andromeda's elegant spiral, its central bulge, its extensive halo, will all be transformed when the Milky Way and Andromeda begin their cosmic dance. The encounter will disturb both galaxies' carefully organized structures, sending stars into new orbits, triggering bursts of star formation, and eventually reshaping two spirals into a single elliptical galaxy. The detailed structure of Andromeda that astronomers have mapped reveals not just a static snapshot, but a dynamic system with a past, present, and future. The rings in its disk tell of past collisions. The streams of stars around it record ongoing gravitational interactions, and its trajectory toward the Milky Way promises future transformation on a scale neither galaxy has experienced for billions of years. As we study Andromeda's structure, we gain perspective on our own galactic home. The Milky Way, viewed from Andromeda, would appear as another spiral galaxy with its own unique features and character. An astronomer on a planet orbiting a star in Andromeda would see our galaxy as we see this, our distant spiral. Its detailed structure visible only through powerful telescopes, its future bound to their own galaxy through gravity's invisible threads. The precision with which we have mapped Andromeda's structure represents one of humanity's great scientific achievements. From a faint smudge in the night sky, described by Persian astronomers a millennium ago as a little cloud, we have resolved a galaxy of 1 trillion stars, mapped its spiral arms, catalogued its satellite galaxies, and measured its motion through space. This achievement speaks to the power of human curiosity and ingenuity, using the faint light that reaches Earth to reconstruct a vast cosmic structure millions of light years away. This detailed understanding has implications beyond pure knowledge. By studying Andromeda's structure and comparing it with the Milky Way and other galaxies, astronomers develop and refine theories of galaxy formation and evolution that apply throughout the universe. Andromeda serves as a crucial test case for these theories, close enough to study in detail, but distinct enough from the Milky Way to provide meaningful comparisons. As astronomical instruments continue to improve, our view of Andromeda's structure grows ever more detailed. Adaptive optics systems on ground-based telescopes now correct for atmospheric distortion, providing images almost as sharp as those from space telescopes. Interferometry combines the light from multiple telescopes to achieve even higher resolution. And planned facilities like the James Webb Space Telescope promise to reveal Andromeda's structure in unprecedented detail across multiple wavelengths. One of the most ambitious efforts to map Andromeda's structure was the panchromatic Hubble Andromeda Treasury, which used the Hubble Space Telescope to observe over 1/3 of Andromeda's disk in 6 wavelength bands. This project resolved more than 100 million individual stars, creating the most detailed portrait ever of a spiral galaxy beyond our own. The resulting dataset continues to yield new insights into Andromeda's structure, star formation history, and stellar populations. Future observations with next-generation facilities will push our understanding of Andromeda's structure to new levels. The Nancy Grace Roman Space Telescope, with its wide field of view, will be able to map Andromeda's outer regions in unprecedented detail. The James Webb Space Telescope will penetrate the galaxy's dust to reveal hidden structures in its disk. And ground-based extremely large telescopes with primary mirrors 30 meters or larger will resolve individual stars even in Andromeda's densest regions. As we conclude our exploration of Andromeda's structure, we return to the perspective of the night sky observer. That faint oval of light visible on dark nights represents not just a distant object, but a complex cosmic ecosystem. Trillion stars organized into bulge, disk, and halo. Hundreds of globular clusters. Dozens of satellite galaxies. Vast regions of star-forming gas. And an enormous dark matter halo extending far beyond the visible galaxy. All of this, bound together by gravity, is moving inexorably toward our own galaxy at over 100 kilometers every second. Two galaxies, so alike and yet destined to become one. When we gaze at Andromeda through a telescope, we see a luminous spiral suspended against the blackness of space. When we look at the Milky Way from Earth, we see a band of light arching across the night sky. But what lies between these islands of stars? What fills the vast gulf that separates our galaxy from Andromeda? Is it truly empty? A void without substance or character? Tonight, we explore the space between galaxies, a realm that is neither as empty nor as uneventful as it might first appear. The distance between the Milky Way and Andromeda spans approximately 2.5 million light-years. This means that light, traveling at 300,000 kilometers per second, the fastest speed possible in our universe, takes 2.5 million years to cross from one galaxy to the other. If we could somehow travel at 1% the speed of light far beyond our current technological capabilities, the journey would still require 250 million years, longer than the time since dinosaurs walked the Earth. This immense distance creates an impression of absolute separation. The two galaxies appear as distinct entities, isolated from each other by an unbridgeable void. But this perception is incomplete. The space between galaxies, while certainly vast and rarefied compared to the interiors of galaxies themselves, is not truly empty. It contains matter, energy, and fields that connect cosmic structures across enormous distances. Perhaps the most obvious component of intergalactic space is light itself. Photons stream in all directions across the cosmos, carrying information from distant sources. Some of this light comes from nearby stars in the Milky Way. Some has traveled from Andromeda, and some has journeyed for billions of years from galaxies far beyond our local group. This omnipresent bath of photons fills every cubic centimeter of space, creating a faint but detectable glow that permeates the universe. Beyond visible light, intergalactic space is filled with radiation across the electromagnetic spectrum. Radio waves from distant quasars, X-rays from hot gas, infrared radiation from dust-enshrouded galaxies, and gamma rays from energetic cosmic events all traverse the gulf between galaxies. The most pervasive of all is the cosmic microwave background radiation, the thermal afterglow of the Big Bang itself, which fills all of space with microwave photons, providing a faint cosmic background temperature of approximately 2.7 Kelvin. But intergalactic space contains more than just radiation. Matter, though incredibly diffuse, exists throughout the cosmic void. The most abundant form is atomic hydrogen, individual protons and electrons that have not combined into more complex structures. This intergalactic hydrogen is exceedingly sparse, with typical densities between 1 and 10 atoms per cubic meter. For comparison, the air we breathe contains approximately 25 sextillion atoms per cubic meter density, roughly 1 sextillion times greater. Despite its rarefied nature, this intergalactic medium is significant due to the enormous volume it occupies. Over large enough distances, even this tenuous material becomes substantial. If we could somehow collect all the atomic matter in the space between the Milky Way and Andromeda, it would likely have enough mass to form millions of stars. Far from being empty, intergalactic space contains vast, diffuse reservoirs of matter that can, under the right circumstances, eventually find its way into galaxies. Interspersed with this atomic hydrogen are heavier elements: carbon, oxygen, silicon, iron produced in stellar furnaces, and scattered into intergalactic space by supernovae and galactic winds. These metals, as astronomers call elements heavier than hydrogen and helium, represent a cosmic memory of stellar lives and deaths. Their presence and abundance in intergalactic space reveal how effectively galaxies can expel material back into the cosmic void. More exotic forms of matter also inhabit the space between galaxies. Cosmic race atomic nuclei accelerated to nearly the speed of light by supernovae, black holes, and other energetic phenomena travel for millions of years across intergalactic space before eventually colliding with other matter. These high-energy particles, primarily protons but including heavier nuclei as well, fill space with a sparse but energetic component that interacts with magnetic fields and other particles. Neutrinos, nearly massless subatomic particles produced in enormous numbers by nuclear reactions in stars and supernova stream across the cosmos, barely interacting with ordinary matter. Trillions of neutrinos pass through your body every second, most originating from our sun, but some having traveled from distant galaxies. These ghostly particles fill intergalactic space with an almost undetectable presence, carrying information about nuclear processes across billions of light years. Perhaps the most significant component of intergalactic space, yet the most difficult to detect directly, is dark matter, an invisible substance that reveals itself only through its gravitational effects. While dark matter concentrates in and around galaxies, it also extends far into intergalactic space, forming tenuous bridges and filaments that connect cosmic structures. This invisible web contains the majority of the matter in the universe and shapes the large-scale distribution of galaxies. Between the Milky Way and Andromeda stretches a vast region of dark matter, its density increasing gradually as it approaches either galaxy. This dark matter forms a gravitational tether between the two spirals, guiding their motion and drawing them inexorably toward each other. Without this unseen connection, the galaxies would likely drift apart with the expanding universe, rather than moving toward their eventual collision. Intergalactic space also contains magnetic fields incredibly weak compared to those we might generate on Earth or measure around planets, but extending over enormous distances. These fields, typically less than 1/1,000,000th of the Earth's magnetic field strength, nevertheless influence the motion of charged particles across vast regions. The space between the Milky Way and Andromeda likely contains complex magnetic structures that record the history of both galaxies' evolution and interaction. One of the most surprising discoveries about intergalactic space in our local group is the presence of isolated stars not bound to any galaxy, but drifting alone through the void. These intergalactic wanderers, sometimes called orphan stars, likely formed within galaxies but were ejected by gravitational interactions, perhaps during close encounters between galaxies or due to the gravitational effects of supermassive black holes. Astronomers estimate that as many as half of all stars in the universe may exist in these intergalactic regions, outside the boundaries of conventional galaxies. Between the Milky Way and Andromeda, millions or even billions of such stars may drift through the darkness, each a solitary sun far from any galactic structure. From such a star, the night sky would appear strikingly different, with the Milky Way and Andromeda visible as two distant galaxies rather than one, appearing as a band of light across the sky, and the other as a faint smudge. More substantial objects may also inhabit intergalactic space. Globular cluster spherical collections of hundreds of thousands of stars that typically orbit galaxy scan, sometimes be torn from their host galaxies by gravitational interactions. These orphan clusters then drift through intergalactic space, compact islands of stars suspended in the cosmic void. Several such clusters have been identified in the local group, tracing orbits that belong to neither the Milky Way nor Andromeda. Even larger structures can exist between galaxies. Astronomers have discovered tidal dwarf galaxies, small galaxies formed from material torn out of larger galaxies during close encounters. These objects, composed primarily of gas and young stars, represent a new class of galaxy born from the interaction between larger systems. While none are known to exist between the Milky Way and Andromeda, similar objects may form when the two galaxies begin their merger in the distant future. The most substantial concentrations of ordinary matter in intergalactic space occur in filaments of warm-hot intergalactic medium, or WIM. This material, heated to temperatures between 100,000 and 10 million Kelvin by gravitational compression and shock waves, forms tenuous structures that trace the underlying distribution of dark matter. These filaments, detectable through their faint X-ray emission and absorption of light from background sources, contain as much as half of all ordinary matter in the universe. Between the Milky Way and Andromeda, the intergalactic medium is structured by the local group's gravitational field. Rather than being uniformly distributed, the gas concentrates along filaments and sheets that connect the larger galaxies. This cosmic web of gas and dark matter forms the underlying structure upon which visible galaxies are arrayed, like luminous nodes in a vast, invisible network. The properties of intergalactic space are not constant but evolve over cosmic time. In the early universe, the intergalactic medium was much denser and more uniform, as matter had not yet collapsed into distinct galaxies. As structure formed under gravity's influence, the universe became increasingly lumpy, with dense galaxies separated by relatively empty voids. The space between the Milky Way and Andromeda has grown increasingly empty over billions of years, as both galaxies have accreted material from their surroundings. In the vast theater of the cosmos, a spectacular performance is scheduled. Two spiral galaxies, each containing hundreds of billions of stars, are moving toward each other across the void. In approximately 4.5 billion years, the Milky Way and Andromeda will begin a gravitational dance that will forever alter both galaxies. This cosmic collision, unfolding over hundreds of millions of years, represents the most dramatic event in our galaxy's Futura transformation that will rewrite the night sky and reshape our cosmic neighborhood. The approaching collision between the Milky Way and Andromeda is not merely theoretical speculation. It is an astronomical certainty, predicted by careful measurements of Andromeda's motion relative to our galaxy. Unlike most distant galaxies, which are moving away from us due to the expansion of the universe, Andromeda shows a blue shift in its spectrumividence, that it is approaching rather than receding. The measured velocity of approach is approximately 110 kilometers per second, or nearly 400,000 kilometers per hour. At this speed, Andromeda travels roughly 10 million kilometers closer to the Milky Way each day. While this might seem rapid on human scales, the initial separation of 2.5 million light-years ensures that the journey will take billions of years. When the collision finally begins, Earth's sun will be in the final stages of its main sequence life, having grown hotter and more luminous with age. The oceans may have already boiled away from our planet's surface, rendering Earth uninhabitable to life as we know it. The term collision might conjure images of violent impacts and catastrophic destruction, but galactic collisions unfold very differently from collisions between solid objects. Galaxies are mostly empty space. The average distance between stars is so vast, typically several light-years, that direct collisions between stars are extremely rare, even when galaxies pass through each other. If we could somehow observe the entire collision from beginning to end, we would see the galaxy's stars flow past each other, like two swarms of fireflies passing in the night. This is not to say the collision will be without dramatic effects. While the stars themselves rarely collide, the galaxies as systems will be profoundly transformed by their encounter. The gravitational interaction between the two galaxies will distort their shapes, redistribute their stars into new orbits, compress gas clouds to trigger bursts of star formation, and eventually merge the two spirals into a single, larger galaxy. It is not destruction, but transformation, a cosmic metamorphosis driven by gravity's inexorable pull. The collision will unfold in several distinct phases, each with its own character and consequences. The first phase has already begun, the long approach, during which the galaxies move toward each other across intergalactic space. During this phase, which will continue for the next 4 billion years, the galaxies remain essentially unchanged in appearance, though their motion through the intergalactic medium may create subtle effects detectable with sensitive instruments. The second phase will begin when the outer regions of the two galaxies make their first contact. The Milky Way and Andromeda both possess extended halos of stars and gas that reach far beyond their visible disks. These tenuous outer regions will be the first to interact, approximately 4.5 billion years from now. As they interpenetrate, stars from each galaxy will begin to feel the gravitational influence of the other, subtly altering their orbits and setting the stage for more dramatic changes to come. As the galaxies continue to approach, their mutual gravitational attraction will accelerate, drawing them together more rapidly. Approximately 4.7 billion years from now, the main disks of the two galaxies will make their first close approach, not a direct collision, but a glancing encounter as Andromeda slides past the Milky Way. This passage will dramatically distort both galaxies, drawing out long tidal tails of stars and gas, and triggering waves of compression in the interstellar medium. This first close approach will be followed by a temporary separation. Like two dancers executing a complex figure, the galaxies will swing around each other and move apart again before gravity pulls them back for a second encounter. This oscillation results from the conversion of gravitational potential energy into kinetic energy as the galaxies accelerate toward each other, then back into potential energy as they move apart. With each pass, however, energy dissipates through the complicated interactions of stars and gas, causing the oscillations to dampen. The effects of even this first encounter will be spectacular. Computer simulations predict that long tidal tails will extend from both galaxies, stretching millions of light-years across intergalactic space. These tails, containing billions of stars torn from the galaxy's disks by gravitational tides, will arc gracefully across the void, creating luminous bridges between the separating galaxies. From within either galaxy, the night sky would be transformed, with the other galaxy appearing as an enormous, distorted spiral spanning a significant portion of the heavens. As the galaxies separate after their first encounter, their shapes will be permanently altered. The elegant spiral patterns that currently characterize both galaxies will be severely disrupted, with stars and gas thrown into new, more chaotic orbits. The precise symmetry of spiral arms will give way to distorted, asymmetric structures reflecting the gravitational violence of the encounter. Both galaxies will begin to lose their distinctive spiral identity, transitioning toward the amorphous form that will characterize the eventual merged system. Approximately 5 billion years from now, the two galaxies will swing back together for a second close approach. By this time, both will be significantly distorted from their original forms, their spiral patterns largely erased by the first encounter. This second pass will further mix the two galaxies' stars and gas, accelerating the merger process. With each subsequent oscillation, the galaxies will lose more of their separate identities, gradually blending into a single, combined system. Throughout these repeated encounters, the interstellar gas within both galaxies will experience profound effects. Unlike stars, which rarely collide due to their small size relative to the distances between them, gas clouds can directly interact, colliding and compressing. These collisions trigger shock waves that compress gas to high densities, creating ideal conditions for the formation of new stars. The merger will thus be accompanied by significant bursts of star formation, far exceeding the current rate in either galaxy. These starbursts will not be uniformly distributed, but concentrated in regions where gas compression is greatest, typically near the center of the merging system, and along features called tidal bridges that connect the interacting galaxies. The newly formed stars will be predominantly massive, hot, and bright, giving the merging galaxies a bluer appearance and significantly increased luminosity. For a relatively brief period, perhaps a few 100 million years, the merging system may shine several times brighter than either original galaxy. The fate of the solar system during this cosmic collision depends on its location in the Milky Way when the merger begins. Currently, our Sun orbits approximately 26,000 light-years from the galactic center, roughly halfway between the center and edge of the visible disk. If the solar system remains in a similar position for the next 4 billion years, it will likely experience significant gravitational perturbations during the merger, but avoid the regions of most intense disturbance near the centers of the merging galaxies. Computer simulations suggest approximately a 70% chance that the solar system will be thrown into a more distant orbit from the center of the merged galaxy. There is a smaller probability, perhaps 20 to 30%, that it might be ejected into a tidal tail, becoming part of a stream of stars arcing through intergalactic space. And there is a very small chance, less than 1%, that the solar system could be drawn toward the galactic center, entering a region of greater stellar density and more frequent close encounters with other stars. Regardless of the solar system's fate, the night sky as seen from Earth would be transformed beyond recognition. The familiar band of the Milky Way would be distorted and eventually replaced by a more diffuse, irregular distribution of stars. Andromeda, currently visible only as a faint smudge in the constellation that bears its name, would grow to dominate the heavens, appearing larger than the full moon and showing visible structure, even to the naked eye. As the merger progressed, the two distinct galaxies would gradually blend, creating new patterns of light, unlike anything in Earth's history. The supermassive black holes at the centers of the Milky Way and Andromeda will play crucial roles in the merger process. Each galaxy harbors a black hole of enormous mass, approximately 4 million solar masses in the Milky Way and 100 to 200 million solar masses in Andromeda. As the galaxies merge, these black holes will sink toward the center of the combined system due to a process called dynamical friction, eventually forming a binary system orbiting their common center of mass. This black hole binary may remain stable for an extended period, perhaps hundreds of millions of years. Eventually, however, the emission of gravitational waves ripples in spacetime predicted by Einstein's general theory of relativity and detected for the first time in 2015 will cause the binary to lose energy and the black holes to spiral together. Their final merger will release an enormous amount of energy in the form of gravitational waves, briefly outshining the entire galaxy in this invisible form of radiation. Throughout the merger process, the distribution of dark matter, the invisible substance that makes up approximately 85% of the matter in both galaxies, will play a crucial role in guiding the interaction. Dark matter halos extend far beyond the visible portions of both galaxies and will be the first components to interact. The merging of these halos will establish the gravitational foundation for the combined galaxy, influencing the redistribution of stars and gas throughout the system. The merger will also affect the satellite galaxies that orbit both the Milky Way and Andromeda. The Milky Way currently hosts several dozen known satellite galaxies, including the Large and Small Magellanic Clouds, while Andromeda possesses its own system of satellites, including the prominent galaxies M32 and M110. As the main galaxies merge, these satellite systems will be disrupted. Some satellites will be captured into new orbits around the combined galaxy. Others might merge with the main system or be ejected into intergalactic space. A few might collide with each other, creating smaller mergers within the larger cosmic dance. Beyond the satellite galaxies, the merger will influence the entire local group, the collection of more than 50 galaxies, to which both the Milky Way and Andromeda belong. The combined gravitational influence of the merged galaxy, sometimes called Milkomeda by astronomers, will be greater than that of either original galaxy. This increased gravitational pull may capture additional satellite galaxies, accelerate the eventual merger of the local group into a single system, and alter the local group's motion relative to other galaxy clusters. The fate of the Triangulum galaxy, also known as M33, is particularly interesting in this context. As the third largest galaxy in the local group, Triangulum could potentially remain separate from the Milky Way-Andromeda merger, becoming a more distant satellite of the combined system. Alternatively, it might participate in the merger, creating a three-way collision that would further complicate the dynamics and outcome. Recent observations suggest Triangulum is bound to Andromeda and may merge with it before Andromeda reaches the Milky Way, effectively creating a two-stage merger process. The long-term outcome of the collision, following hundreds of millions of years of complex gravitational interactions, will be a single, massive galaxy of a different type than either the Milky Way or Andromeda. While both original galaxies are spirals, characterized by flattened disks and spiral arms, the merged galaxy will likely be an elliptical galaxy, a more three-dimensional, football-shaped distribution of stars, without clear structural features, like spiral arms or a distinct disk. This transformation from spiral to elliptical reflects a fundamental change in the orbits of stars. In spiral galaxies, most stars follow roughly circular orbits in a common plane, creating the characteristic disk shape. During a galactic merger, gravitational interactions scatter stars into more random, eccentric orbits oriented in all directions. The resulting elliptical galaxy contains stars moving on these varied orbits, creating a more spheroidal shape, without the organized motion necessary to maintain spiral structure. The transition from spiral to elliptical, also typically involves changes in star formation. Spiral galaxies like the Milky Way and Andromeda contain significant reservoirs of cold gas, the raw material for new star sand, continue to form stars at modest rates. Elliptical galaxies, by contrast, generally contain less cold gas and form few, if any, new stars. They appear redder than spiral galaxies because they are dominated by older stellar populations rather than newly formed blue stars. This pattern suggests that the merger of the Milky Way and Andromeda will proceed through several distinct phases with respect to star formation. Initially, the collision will trigger significant star formation as gas clouds compress and collapse. This starburst phase might last several 100 million years, producing a blue, highly luminous system. As the merger progresses, however, much of the gas will either be converted to stars or heated and ejected from the galaxy. Without cold gas to form new stars, the merged galaxy will gradually redden as its stellar population ages. The transformation of two spiral galaxies into a single elliptical has been observed in many other galactic systems at various stages of merger. Astronomers classify these interacting systems according to their progress along the merger sequence. From early-stage systems showing initial distortions through actively merging pairs with dramatic tidal features, to late-stage systems where the original galaxies are no longer distinguishable. This sequence, observed across billions of light-years of cosmic history, provides a preview of what awaits the Milky Way and Andromeda. Among the most famous examples of merging galaxies are the antennae galaxies, located approximately 45 million light-years from Earth in the constellation Corvus. This system, also known as NGC 4038 and NGC 4039, consists of two spiral galaxies in an advanced stage of collision. Long tidal tails extend from the merging galaxies, resembling insect antennae, and giving the system its common name. Observations of the antennae galaxies reveal intense star formation triggered by the merger, with numerous young star clusters visible in the overlapping regions. Another well-known example is the Mice galaxies, or NGC 4676 and NGC 4675, located approximately 300 million light-years away in the constellation Coma Berenices. These galaxies, in an earlier stage of interaction than the antennae, display characteristic tidal tails that give them a mouse-like appearance. The Mice provide a preview of what the Milky Way and Andromeda might look like shortly after their first close approach, with spiral structure still visible but significantly distorted by gravitational interaction. By studying these and other merging systems, astronomers can reconstruct the likely sequence of events awaiting the Milky Way and Andromeda. Computer simulations incorporate the observed properties of both galaxies, their masses, sizes, rotation curves, gas content, and relative velocity to predict the detailed evolution of the collision. These simulations, running on powerful supercomputers, track the motion of millions of particles representing stars, gas clouds, and dark matter under the influence of gravity and other relevant forces. The results of these simulations provide a cosmic preview of our galactic future. They show the approach of Andromeda as a gradually swelling spiral in our night sky. They depict the first close passage, with both galaxies distorting and throwing out long tidal tails. They illustrate the temporary separation, followed by subsequent encounters, each more intimate than the last. And they reveal the final merger, with two spiral galaxies transformed into a single elliptical system over the course of 1 billion years or more. While the broad outlines of this process are well understood, many details remain uncertain and subject to ongoing research. The exact timing of the first encounter depends on Andromeda's tangential velocity, its motion perpendicular to our line of sight, which is more difficult to measure than its radial velocity toward us. Recent measurements suggest the first close approach may occur slightly later than previously estimated, perhaps 5 billion years from now, rather than 4.5 billion. The collision may also be more direct than earlier models suggested, potentially accelerating the merger process. How do astronomers predict the future collision between the Milky Way and Andromeda with such confidence? We cannot observe the complete merger of galaxies in real time. Such events unfold over hundreds of millions of years, far beyond human timescales. Yet scientists speak with remarkable certainty about the approaching collision, describing its timeline, stages, and ultimate outcome in detail. This confidence stems from a powerful tool of modern astronomy: computer simulations that model the complex gravitational interactions between galaxies and predict their evolution across cosmic time. Simulating galactic collisions represents one of the most sophisticated applications of computational astrophysics. These simulations combine observational data, physical laws, and mathematical models to create virtual galaxies that behave like their real counterparts. By setting these virtual galaxies on collision courses and allowing the laws of physics to dictate their evolution, astronomers can preview cosmic events that would otherwise remain hidden in the distant future or far across the universe. The history of galactic collision simulations extends back to the late 1960s and early 1970s, when pioneering astronomers like Alaa and Juri Toomre first used computers to model the gravitational interactions between galaxies. These early simulations were necessarily simple, representing each galaxy as a collection of a few hundred particles, and neglecting many complex physical processes. Despite these limitations, they successfully reproduced the basic features observed in interacting galaxies, particularly the dramatic tidal tails that extend from such systems. Modern simulations have advanced enormously in sophistication. Today's models represent galaxies with millions or even billions of particles, each tracing the motion of stars, gas clouds, or dark matter under the influence of gravity and other forces. These simulations incorporate detailed physics, including the hydrodynamics of gas, the formation of stars from compressed interstellar material, the feedback effects of supernovae and black holes, and the influence of dark matter on large-scale dynamics. The resulting virtual galaxies capture the complexity and beauty of their real counterparts with remarkable fidelity. To simulate the specific collision between the Milky Way and Andromeda, astronomers begin with the observed properties of both galaxies. These include their masses, sizes, rotation curves, gas content, and current separation and relative velocity. The simulation then places virtual versions of these galaxies at their current positions and allows them to evolve forward in time according to the laws of physics, particularly gravity, which dominates the large-scale dynamics of the interaction. The first challenge in creating these simulations is accurately representing the structure of both galaxies. Each galaxy consists of several components that behave differently during a collision. The stellar disks, the flattened regions containing most of the visible stars, respond to gravitational forces but not to direct collisions, as stars rarely encounter each other even during galactic mergers. The interstellar gas, by contrast, can collide and compress, triggering star formation and generating additional complexity. The central bulges, containing older stars in more random orbits, interact differently than the organized disks. And the dark matter halos, extending far beyond the visible galaxies and containing most of their mass, establish the gravitational foundation for the entire interaction. Each of these components must be accurately modeled to capture the full complexity of the merger. Modern simulations typically represent stars and dark matter as collisionless particles that interact only through gravity. Gas, by contrast, is modeled using computational fluid dynamics techniques that capture its ability to compress, heat, cool, and form stars. The resulting hybrid simulations track both the large-scale gravitational dynamics and the smaller-scale processes that influence gas behavior and star formation. The second challenge lies in the vast range of scales involved in a galactic collision. A complete simulation must accurately represent processes occurring on scales from the formation of individual stars, measured in light years, to the overall dynamics of galaxies, measured in hundreds of thousands of light years. No single computational approach can span this entire range directly, so astronomers use various approximations and multi-scale techniques to capture the most important physical processes at each scale. One common approach is to use adaptive mesh refinement, which divides the simulated volume into cells of varying sizes, with smaller cells in regions where greater detail is needed. Another approach, called smoothed particle hydrodynamics, represents gas as a collection of particles whose properties are smoothed over their neighboring regions. These and other techniques allow simulations to focus computational resources where they are most needed, while maintaining accuracy across the full range of relevant scales. With these approaches in hand, astronomers can create detailed simulations of the Milky Way-Andromeda collision. These simulations begin with the galaxies at their current separation of approximately 2.5 million light-years and track their mutual gravitational attraction, which gradually accelerates their approach. As the galaxies draw closer, their outer regions begin to feel each other's gravitational influence, subtly distorting their shapes. When they make their first close approach, approximately 4.5 billion years from now, dramatic tidal forces create long streamers of stars, extending from both galaxies. The simulations show that this first encounter is likely to be followed by a temporary separation, as the galaxy's momentum carries them past each other. Gravity soon overcomes this motion, however, drawing them back for a second encounter. With each pass, the galaxies lose energy through dynamical frictional process, in which stars and gas clouds are gravitationally deflected, converting orbital energy into random motion. This energy loss causes the galaxies to spiral ever closer, eventually merging completely over the course of approximately 2 billion years from the first encounter. Throughout this process, the simulations track not just the overall motion of the galaxies, but the fate of their individual components. The stellar disks, initially flat and organized, become warped and distorted by tidal forces. Stars are thrown into new, more random orbits, gradually erasing the spiral patterns that characterize the original galaxies. Gas clouds collide and compress, triggering bursts of star formation that create short-lived hot blue stars. Dark matter, responding only to gravity, forms a combined halo that establishes the gravitational potential of the merged system. One of the most striking features revealed by these simulations is the transformation of galactic structure. Both the Milky Way and Andromeda are spiral galaxies, characterized by flattened disks with elegant spiral arms. The merged galaxy, by contrast, is likely to be an elliptical galaxy, a more three-dimensional, football-shaped distribution of stars, without clear features. This transformation results from the gravitational scattering of stars into more random orbits during the merger, erasing the organized motion necessary to maintain a disk and spiral arms. Simulations also reveal the likely fate of the supermassive black holes at the centers of both galaxies. Each galaxy harbors a black hole of enormous mass, approximately 4 million solar masses in the Milky Way, and 100 to 200 million solar masses in Andromeda. As the galaxies merge, these black holes sink toward the center of the combined system due to dynamical friction. They eventually form a binary system, orbiting their common center of mass, before ultimately merging into a single, larger black hole. The merger of these supermassive black holes represents one of the most energetic events in the simulation. As they spiral together, the black holes emit gravitational wave ripples in space-time that carry away energy and angular momentum. In the final moments of their merger, they release an enormous amount of energy in the form of these gravitational waves, briefly outshining the entire galaxy in this invisible form of radiation. Future gravitational wave observatories, more sensitive than current facilities, might detect such events occurring in distant merging galaxies. Another key insight from simulations concerns star formation during the merger. When galaxies collide, the interaction compresses gas clouds, creating ideal conditions for the formation of new stars. The simulations predict that the Milky Way-Andromeda collision will trigger significant bursts of star formation, particularly during close passages when tidal forces are strongest. These starbursts will produce populations of massive, bright stars that significantly increase the galaxy's luminosity, particularly in ultraviolet and blue wavelengths associated with young stellar populations. This enhanced star formation will not be distributed uniformly throughout the merging galaxies, but concentrated in regions where gas compression is greatest. These typically include the central regions, where gas flows inward due to gravitational torques, and along tidal features like bridges and tails, where gas is stretched and compressed by tidal forces. The resulting star formation pattern creates distinctive features visible in simulated images of the merger, with bright knots and filaments of new stars highlighting the regions of most intense activity. Simulations also allow astronomers to explore the fate of specific components within the merging galaxies, such as our own solar system. By tracking the motion of particles initially located at positions similar to the Sun's current location in the Milky Way, scientists can estimate the probability of different outcomes for our cosmic neighborhood. These simulations suggest that the solar system is unlikely to be ejected from the merged galaxy or to approach dangerously close to the galactic center. Instead, it will most likely be thrown into a more distant elliptical orbit around the center of the combined galaxy. To validate these simulations and ensure they accurately predict real galactic collisions, astronomers compare their results with observations of actual merging galaxies at various stages of interaction. The universe contains countless examples of galaxy pairs caught in the act of merging, from systems making their first approach to those in the final stages of combination. By comparing simulated mergers with these real systems, astronomers can refine their models and gain confidence in their predictions for the Milky Way-Andromeda collision. Among the most famous examples of merging galaxies are the antennae galaxies, located approximately 45 million light-years from Earth. This system consists of two spiral galaxies in an advanced stage of collision, with long tidal tails extending from the merging bodies. Detailed observations of the antennae reveal intense star formation triggered by the merger, with numerous young star clusters visible in regions where the galaxies overlap. Simulations of similar collisions successfully reproduce these features, including the characteristic tidal tails and enhanced star formation. Another well-studied example is the Mice galaxies. Located approximately 300 million light-years away, these galaxies, in an earlier stage of interaction than the antennae, display distinctive tidal tails that give them a mouse-like appearance. By adjusting the parameters of simulated galaxy pairs, their masses, gas content, relative velocities, and orbital orientations, astronomers can create virtual systems that closely match the observed properties of the mice, validating the physical models used in their simulations. Beyond these individual examples, large astronomical surveys have identified thousands of interacting and merging galaxies across the observable universe. These systems form a sequence from early-stage interactions showing minor distortions, through actively merging pairs with dramatic tidal features, to late-stage systems where the original galaxies are no longer distinguishable. By comparing simulated mergers with this observed sequence, astronomers can trace the evolution of galaxy interactions across cosmic time and verify that their models correctly capture the dynamics of these complex systems. The validation of simulation methods through comparison with observed mergers gives astronomers confidence in their predictions for the Milky Way-Andromeda collision. While the exact details may vary depending on still uncertain parameters, particularly Andromeda's tangential velocity, the broad outlines of the merger process are well established by both theoretical understanding and observational confirmation of similar events throughout the cosmos. Recent refinements in these simulations, incorporating data from the European Space Agency's Gaia mission and other advanced observatories, have updated our understanding of the approaching collision. Current models suggest the first close approach may occur slightly later than previously estimated, perhaps 5 billion years from now rather than 4.5 billion. The collision may also be more direct than earlier models suggested, potentially accelerating the merger process. And the influence of other members of the local group, particularly the Triangulum Galaxy, M33, may introduce additional complexity to the interaction. Beyond predicting the specific collision between the Milky Way and Andromeda, simulations of galactic mergers contribute to our broader understanding of galactic evolution. They reveal how mergers transform galaxy morphology, triggering the conversion of spirals to ellipticals. They demonstrate the role of mergers in triggering starbursts and fueling central black holes. And they illustrate how the hierarchical assembly of smaller structures into larger ones has shaped the universe we observe today. These simulations also place the future Milky Way-Andromeda collision in a cosmic context. Far from being an unusual event, this merger represents the continuation of a process that has operated throughout cosmic history. The Milky Way itself has absorbed numerous smaller galaxies, as evidenced by stellar streams in its halo, and the ongoing disruption of satellite galaxies like the Sagittarius Dwarf. The approaching collision with Andromeda simply represents a more dramatic example of this ongoing process of galactic growth through mergers. As computational capabilities continue to advance, simulations of galactic collisions grow ever more sophisticated. Modern supercomputers allow astronomers to model galaxies with unprecedented resolution, tracking the motion of billions of particles representing stars, gas, and dark matter. Advanced physical models incorporate processes like magnetohydrodynamics, radiative transfer, and stellar feedback, capturing the complex interplay of forces that shape galactic evolution. And machine learning techniques help analyze the vast amounts of data produced by these simulations, identifying patterns and making predictions with greater accuracy than ever before. One of the most ambitious current projects is the FIRE, Feedback in Realistic Environments, simulation suite, which models galaxy formation and evolution with unprecedented physical detail. These simulations track not just the gravitational interactions between stars and gas, but the complex feedback processes through which stars influence their surroundings, from ultraviolet radiation that ionizes nearby gas to supernova, explosions that inject energy and heavy elements into the interstellar medium. By incorporating these processes, the FIRE simulations, and others like them, create virtual galaxies that closely resemble those we observe in the real universe. Another cutting-edge approach is the illustrious TNG, the Next Generation project, which simulates the evolution of a large volume of the universe from shortly after the Big Bang to the present day. Unlike simulations focused on individual galaxy mergers, illustrious TNG models the formation and evolution of thousands of galaxies simultaneously, capturing the cosmic context in which mergers occur. These cosmological simulations reveal how the large-scale structure of the universe, cosmic web of filaments and voids influences galaxy evolution and merger rates throughout cosmic history. As we look to the future, simulations of galactic collisions will continue to advance in sophistication and accuracy. Future models will incorporate even more detailed physics, higher resolution, and improved handling of complex processes like black hole accretion and feedback. They will benefit from increasingly precise observational constraints, particularly measurements of galactic properties and motions from missions like Gaia and its successors. And they will run on increasingly powerful supercomputers, enabling simulations of unprecedented scale and complexity. These advances promise to refine our understanding of the approaching collision between the Milky Way and Andromeda, providing ever more detailed predictions of its timeline, features, and ultimate outcome. They will help us visualize the night sky as seen from Earth throughout the merger process, from the gradual approach of Andromeda as a swelling spiral in our heavens to the dramatic transformation of the entire sky as the galaxies blend. And they will place this collision in its cosmic context as one event in the ongoing process of structure formation that has shaped our universe since its earliest moments. Through these simulations, we gain a window into our galaxy's futura preview of cosmic events that will unfold long after our own time. We can already see the future painted in stars and slow gravity. As we contemplate the cosmic collision between the Milky Way and Andromeda, a natural question arises. What will happen to our home planet? Will Earth survive this galactic merger? Will life continue? How will our night sky change as these vast spiral galaxies begin their gravitational dance? Tonight, we turn our attention from the grand cosmic scales of galactic evolution to the more intimate question of our own planet's fate during this extraordinary event. First, let us address the most immediate concern. Will Earth be physically destroyed when Andromeda collides with the Milky Way? The answer, perhaps surprisingly, is almost certainly no. Despite the immense scale and energy of a galactic collision, the vast majority of stars in both galaxies will emerge unscathed. This seeming contradiction stems from the enormous distances between stars relative to their sizes. Even in a collision involving hundreds of billions of stars from each galaxy, direct stellar collisions are exceedingly rare. To understand why, consider the scales involved. Stars typically have diameters measured in millions of kilometers, while the distances between neighboring stars are measured in light-years each. Light-year being approximately 9.5 trillion kilometers. In our own stellar neighborhood, the closest star to our Sun, Proxima Centauri, lies about 4.2 light-years away. This means the space between stars is typically millions of times larger than the stars themselves. Imagine two swarms of bees, each containing billions of insects, passing through each other. Despite the enormous number of bees involved, the vast majority would fly through without colliding, simply because the space between individual bees is much larger than the bees themselves. Similarly, when galaxies collide, their stars generally pass by each other, their mutual courses altered by gravity but rarely resulting in direct impacts. This is not to say the collision will have no effect on our solar system. While direct stellar collisions are unlikely, the gravitational influence of the merger will significantly alter stellar orbits throughout both galaxies. Currently, our Sun follows a relatively circular path around the Milky Way's center, completing one orbit approximately every 230 million years. This stable orbital pattern, which has persisted for billions of years, will be disrupted when Andromeda arrives. Simulations suggest that the solar system may be thrown into a more elliptical orbit, potentially carrying it farther from the galactic center than its current position. There is also a small possibility estimated, at less than 5%, that our solar system could be ejected from the merged galaxy entirely, becoming an intergalactic wanderer in the space between galaxies. Most likely, however, Earth and the Sun will remain bound to the merged galaxy, simply following a new orbital path through the transformed cosmic landscape. The collision might also bring other stars relatively close to our solar system. Currently, the closest stellar approach expected in the near future is by a star called Gliese 710, which will pass within about 1.1 light-years of the Sun, in approximately 1.3 million years. During the Milky Way-Andromeda merger, much closer stellar approaches could occur, perhaps as near as a few tenths of a light-year. While still far too distant to directly affect Earth through gravity, such encounters might disturb the Oort Cloud, spherical shell of icy objects surrounding our solar system, potentially sending comets toward the inner planets. Beyond these gravitational effects, another concern might be radiation. Galactic collisions compress gas clouds, triggering bursts of star formation. Many of these newly formed stars are massive, hot, and short-lived, ending their lives as supernovae that release intense radiation. Could Earth be harmed by this increased supernova activity? While the merger will indeed increase the supernova rate in some regions of the combined galaxy, the effect is localized primarily to areas of intense star formation, typically the central regions and specific areas where gas clouds collide. Unless our solar system happens to be relocated to one of these Johnson unlikely scenario based on current simulation sessions, increased supernova rate should not pose a significant threat. Interestingly, by the time the Milky Way and Andromeda begin their merger approximately 4.5 billion years from now, Earth may already be uninhabitable for complex life due to the Sun's natural evolution. Our Sun gradually increases in luminosity as it ages, a process that will cause Earth's oceans to evaporate within approximately 1 to 2 billion years. By the time of the galactic collision, the Sun will be approaching the end of its main sequence lifetime and beginning to expand into a red giant. This stellar evolution will have far more immediate consequences for Earth than the galaxy merger occurring simultaneously. While direct effects on Earth's habitability may be minimal, the merger will dramatically transform our night sky, perhaps the most noticeable change for any observers still present on our planet. Currently, Andromeda appears as a faint, fuzzy patch in the constellation that bears its name, visible only under dark skies and spanning roughly the width of the full moon. As the galaxies draw closer, Andromeda will grow progressively larger and brighter in our sky. By approximately 3.8 billion years from now, Andromeda will span several degrees of the night sky, appearing larger than any constellation and showing visible structure even to the naked eye. The distinctive spiral arms, currently visible only through telescopes, will become apparent without optical aid. Andromeda will no longer be a distant object but a looming presence, a cosmic structure visibly approaching our own galaxy. When the first close approach occurs, approximately 4.5 billion years from now, Andromeda will dominate the night sky. its spiral structure will appear distorted by tidal forces, stretching across a significant portion of the heavens. The Milky Way itself will also begin to distort, its familiar band across the sky warping in response to Andromeda's gravitational pull. For any observers on Earth at this time, the night sky will be unlike anything in human experience here, a spectacular cosmic display of two giant galaxies beginning their gravitational dance. As the merger progresses, the distinct spiral structures of both galaxies will gradually dissolve. The once organized disks will give way to a more chaotic distribution of stars, as gravitational interactions throw stellar orbits into disarray. The night sky will grow increasingly bright as stars from Andromeda mix with those of the Milky Way, their combined light illuminating Earth's nights to a degree unprecedented in our planet's history. In the final stages of the merger, perhaps 6 to 7 billion years from now, the night sky will no longer show any trace of the original spiral galaxies. Instead, a diffuse, roughly elliptical distribution of stars will surround Earth in all directions. The familiar dark band of our galaxy's dust lanes, currently visible as the Milky Way's silhouette against its bright background of stars, will disperse. The cosmos as seen from Earth will be transformed completely, reflecting the birth of a new galactic structure, neither Milky Way nor Andromeda, but a combination of both. This transformation of the night sky represents perhaps the most significant impact the galaxy merger will have on Earth itself. The cosmic backdrop against which human cultures have developed their mythologies, navigation systems, and early sciences will be fundamentally altered. The constellations that have guided sailors and inspired storytellers since ancient times will be disrupted, their stars scattered into new patterns by the gravitational chaos of merging galaxies. Beyond the visible changes to our night sky, the merger might influence Earth in more subtle ways. The increased density of stars in some regions of the merged galaxy could alter the cosmic ray environment of our solar system. Cosmic ray-shy energy particles accelerated by supernovae and other energetic events constantly bombard Earth, contributing to background radiation and potentially influencing cloud formation and other atmospheric processes. Changes in the cosmic ray flux resulting from the galaxy merger might have subtle effects on Earth's climate, though these would likely be minor compared to other factors. Another consideration is the potential awakening of Andromeda's central supermassive black hole. Currently, both the Milky Way's and Andromeda's central black holes are relatively quiet, accreting matter at low rates. During the merger, however, gas may be driven toward the galactic center, potentially fueling these black holes and causing them to enter an active phase. If this occurs, the merged galaxy may temporarily host an active galactic nucleoso-bright, energetic central region powered by the black hole's accretion disk. While not directly threatening to Earth due to its distance from the galactic center, such an active nucleus would add another spectacular feature to our night sky. Despite these various effects, it's important to emphasize that the most significant threats to Earth's habitability come not from the galaxy merger, but from processes much closer to home. The sun's increasing luminosity, which will eventually boil away Earth's oceans, represents a far more immediate challenge to our planet's habitability than any consequence of the Milky Way-Andromeda collision. Similarly, potential asteroid or comet impacts, while rare, pose a more direct threat to life on Earth than the distant gravitational perturbations of merging galaxies. As the cosmic dance between the Milky Way and Andromeda reaches its final movements, the distinct spiral structures that once characterized both galaxies will have dissolved. In their place, a new galactic form will emerge neither spiral nor irregular, but elliptical in shape. Astronomers have given this future galaxy a name that honors its dual heritage, Milkomeda, a linguistic blend of Milky Way and Andromeda. Tonight, we explore the birth of this new galaxy and the cosmic processes that will transform two majestic spirals into a single, massive, elliptical system. The formation of Milkomeda will not be an instantaneous event, but the culmination of a merger process lasting approximately 2 billion years from the first close approach of the parent galaxies. Throughout this extended period, the Milky Way and Andromeda will make multiple passes by each other, each encounter drawing them closer and more thoroughly mixed. With each pass, stars will be thrown into increasingly randomized orbits, gradually erasing the organized motion that maintained the galaxy's spiral structures. By approximately 6.5 billion years from now, the two galaxies will have fully coalesced. Where once two spiral disks rotated majestically through space, a single, roughly football-shaped distribution of stars will remain. This transformation from spiral to elliptical represents one of the most fundamental changes in galactic morphology, cosmic metamorphosis, driven by gravitational interactions and the conservation of energy and angular momentum. The key to understanding this transformation lies in the organization of stellar orbits. In spiral galaxies like the Milky Way and Andromeda, most stars follow roughly circular paths around the galactic center, all moving in the same direction within a relatively flat disk. This organized, rotational motion creates and maintains the characteristic spiral structure. During a galactic merger, however, gravitational interactions between the galaxies disrupt this orderly movement, scattering stars into more random, three-dimensional orbits. Imagine two spinning frisbees colliding in mid-air. Their flat, rotating forms would be disrupted by the impact, with pieces scattered in all directions. Similarly, when spiral galaxies merge, their rotating disks are disrupted, with stars scattered into orbits that take them far above and below the original galactic planes. The resulting elliptical galaxy contains stars moving in all directions, their orbits oriented randomly rather than aligned in a disk. This transformation can be understood in terms of energy and angular momentum. When the galaxies merge, the ordered rotational energy of their disks is converted into random motion. Angular momentum, which must be conserved, is redistributed from the organized rotation of the disks to the more chaotic motions of individual stars. The total energy and angular momentum remain the same, but their distribution changes fundamentally, resulting in a structurally different type of galaxy. The physical size of Milkomeda will exceed that of either parent galaxy alone. While the Milky Way spans approximately 100,000 light-years in diameter and Andromeda approximately 220,000 light-years, the merged elliptical galaxy will extend roughly 300,000 light-years across its longest axis. This increase reflects the redistribution of stars into more extended orbits during the merger process, causing the galaxy to puff up into a more three-dimensional shape. The mass of Milkomeda will approximately equal the combined mass of the Milky Way and Andromeda, minus any material ejected into intergalactic space during the merger. Current estimates suggest the Milky Way contains approximately 1 to 1.5 trillion solar masses, including dark matter, while Andromeda contains about 2 trillion solar masses. The merged galaxy will therefore have a total mass of roughly 3 to 3.5 trillion solar masses, making it one of the most massive galaxies in the local universe. The stellar population of Milkomeda will reflect its dual heritage, containing stars originally formed in both parent galaxies as well as new stars born during the merger process. The oldest stars, those already ancient when the collision began, will have ages exceeding 20 billion years by the time Milkomeda fully forms. These stellar elders, primarily low-mass red dwarfs that burn their fuel extremely slowly, will serve as living fossils of the pre-merger galaxies, preserving in their composition and motion echoes of the spirals that once contained them. Alongside these ancient stars, Milkomeda will host stellar populations of various ages, including stars formed during the collision itself. When galaxies merge, their gas clouds collide and compress, triggering bursts of star formation. These collision-induced starbursts create new generations of stars, particularly massive, bright stars that evolve quickly and die spectacularly as supernovae. By the time Milkomeda fully forms, most of these massive stars will have already completed their life cycles, leaving behind neutron stars and black holes as remnants. The distribution of stars within Milkomeda will differ significantly from that of its spiral predecessors. Rather than being concentrated in a disk with spiral arms, stars will be arranged in a roughly ellipsoidal distribution, more densely packed near the center and gradually thinning toward the outer regions. This distribution follows a mathematical pattern known as the de Vaucouleurs profile, or the R to the 1/4 law, characteristic of elliptical galaxies throughout the universe. One of the most significant differences between Milkomeda and its spiral parents will be the reduced presence of gas and dust. Spiral galaxies typically contain substantial reservoirs of cold hydrogen gas, the raw material from which new stars form. During the merger, much of this gas will either be converted to stars in collision-induced starbursts or heated and expelled from the galaxy by energetic processes like supernova explosions. The resulting elliptical galaxy will contain far less cold gas, limiting its ability to form new stars. This depletion of star-forming material will fundamentally alter Milkomeda's character. Unlike the Milky Way and Andromeda, which continue to form new stars at modest rates, approximately 1 to 3 solar masses per year, Milkomeda will experience very little ongoing star formation. Without the bright blue massive stars that dominate the light output of spiral arms, the merged galaxy will appear redder and less luminous relative to its mass than its spiral predecessors. The central region of Milkomeda will host a particularly interesting feature, a supermassive black hole formed from the merger of the Milky Way's and Andromeda's central black holes. Currently, the Milky Way contains a black hole of approximately 4 million solar masses, while Andromeda's central black hole is estimated at 100 to 200 million solar masses. As the galaxies merge, these black holes will sink toward the center of the combined system due to dynamical frictional process, where gravitational interactions with surrounding stars gradually draw massive objects toward the galactic center. Once both black holes reach the central region, they will form a binary system orbiting their common center of mass. This binary may persist for an extended period, perhaps hundreds of millions of years, before gravitational waves ripples in spacetime carry away enough energy to cause the black holes to spiral together and merge. The final merger will release an enormous amount of energy in the form of gravitational waves, briefly outshining the entire galaxy in this invisible form of radiation. The merged supermassive black hole, with a mass exceeding 200 million solar masses, will influence its surroundings through its powerful gravitational field. Stars in the central few light years will orbit at extremely high velocities, potentially exceeding 1,000 kilometers per second. Some stars may be torn apart by tidal forces as they pass too close to the black hole, creating brief flares of radiation as their material is accreted. Others may be ejected from the galaxy entirely through gravitational interactions with the black hole, becoming hypervelocity stars racing through intergalactic space. Beyond the central regions, Milkomeda will develop a vast halo of stars, extending hundreds of thousands of light years from its center. This halo, more extensive than those of either parent galaxy, will contain primarily older stars on highly elliptical orbits. These stars, scattered to large distances during the merger process, will orbit Milkomeda like a swarm of bees, moving in all directions rather than in an organized rotation. Some may take billions of years to complete a single orbit, reaching distances of up to 1 million light years from the galactic center at their farthest points. Interspersed throughout this stellar halo will be globular cluster spherical collections of hundreds of thousands of stars that orbit the galaxy as a unit. Both the Milky Way and Andromeda currently host substantial populations of these ancient star clusters, with the Milky Way containing approximately 150 and Andromeda over 400. Most of these will survive the merger intact, combining to give Milkomeda an impressive system of more than 500 globular clusters orbiting within its halo. The fate of the satellite galaxies currently orbiting the Milky Way and Andromeda presents another fascinating aspect of Milkomeda's formation. Both spiral galaxies currently host dozens of smaller satellite galaxies. The Milky Way's entourage includes the large and small Magellanic Clouds, while Andromeda's includes prominent satellites like M32 and M110. During the merger, these satellite systems will be disrupted, with complex outcomes depending on each satellite's position and velocity when the collision occurs. Some satellites will be captured into new orbits around the merged galaxy, continuing their existence as distinct systems within Milkomeda's gravitational influence. Others will be torn apart by tidal forces, their stars becoming incorporated into Milkomeda itself. A few might even be ejected from the system entirely, becoming isolated dwarf galaxies wandering through intergalactic space. The most likely scenario involves a mixture of these outcomes, with Milkomeda ultimately retaining a significant but reduced system of satellite galaxies compared to the combined total of its predecessors. The dark matter distribution of Milkomeda will reflect its dual heritage as well. Both the Milky Way and Andromeda are embedded within extensive halos of dark matter-invisible material detectable only through its gravitational effects. These halos, extending far beyond the visible galaxies, contain the majority of both systems' mass. As the galaxies merge, their dark matter halos will combine to form a single, roughly spherical distribution centered on the merged galaxy. This dark matter halo will play a crucial role in determining Milkomeda's structure and dynamics. Its gravitational field will govern the orbits of stars throughout the galaxy, particularly in the outer regions where dark matter dominates over visible matter. The combined halo will extend several million light-years from the galaxy's center, gradually blending into the larger dark matter structure of the local group and beyond. The formation of Milkomeda will not occur in isolation, but as part of the larger evolution of the local group, the collection of galaxies to which both the Milky Way and Andromeda belong. This group, containing more than 50 galaxies of various sizes, is itself evolving toward an eventual merger of all its members. The formation of Milkomeda represents the first major step in this process, combining the group's two largest members into a single dominant galaxy. Following the Milky Way-Andromeda merger, the next significant event will likely involve the Triangulum Galaxy, M33, currently the third largest galaxy in the local group. Triangulum, a spiral galaxy about 60,000 light-years across, may either merge with Milkomeda or continue orbiting it as a satellite, depending on its velocity and position during the earlier merger. Recent observations suggest Triangulum is gravitationally bound to Andromeda and may merge with it before the Milky Way-Andromeda collision begins, potentially creating a three-way merger rather than the two-stage process described here. Regardless of the precise sequence, the long-term fate of the local group appears to be a gradual coalescence of its members into a single massive galaxy, dominated by the combined matter of what are currently separate systems. This process, unfolding over tens of billions of years, represents the natural evolution of gravitationally bound galaxy groups in an expanding universe. While cosmic expansion carries most galaxies away from each other, those bound in groups and clusters merge over time, creating increasingly massive but fewer individual galaxies. The formation of Milkomeda also occurs within the context of the evolving universe. By the time the merged galaxy fully forms, approximately 6.5 billion years from now, the universe itself will be nearly 20 billion years old, almost 1.5 times its current age. The cosmic expansion will have carried most distant galaxies significantly farther away, making them fainter and redder from our perspective. The cosmic microwave background, the afterglow of the Big Bang, will have cooled further, making it more difficult to detect, and the accelerating expansion driven by dark energy will have further isolated the local group from the broader cosmic neighborhood. Within this evolving cosmic context, Milkomeda will enter a quieter phase of galactic evolution. Without significant reserves of cold gas to fuel star formation, the merged galaxy will gradually grow more quiescent. Star formation will not cease entirely. Some gas will continue to cool and collapse, particularly material falling into the galaxy from intergalactic space, but it will proceed at a much reduced rate compared to spiral galaxies. This decline in star formation represents a kind of cosmic middle age for Milkomeda, a transition from the active youth of its spiral predecessors to the more sedate maturity of an elliptical galaxy. As star formation declines, the character of Milkomeda's stellar population will gradually change. The massive, bright, blue stars that dominate the light output of spiral arms have short lifespans, living only millions to tens of millions of years before exploding as supernovae. Without ongoing star formation to replenish these luminous giants, they will gradually disappear from Milkomeda's stellar inventory. The galaxy's light will become increasingly dominated by longer-lived, less massive stars, particularly red giants and red dwarfs, giving it a distinctly redder appearance than either of its spiral ancestors. This reddening of Milky-Meda's stellar population reflects a fundamental change in the galaxy's energy output. Young, massive stars emit primarily in blue and ultraviolet wavelengths, while older, less massive stars emit more in the red and infrared. As Milky-Meda ages without significant new star formation, its spectral energy distribution will shift toward longer wavelengths, with an increasing proportion of its light emitted in the red and infrared portions of the spectrum. Despite this overall trend toward quiescence, Milky-Meda may experience occasional bursts of activity, triggered by interactions with satellite galaxies or the accretion of gas clouds from intergalactic space. These events, while not comparable to the dramatic merger that formed the galaxy, can temporarily rejuvenate star formation in localized regions. They represent the cosmic equivalent of second-act brief revivals of activity in an otherwise increasingly quiet system. The central supermassive black hole may also experience periods of increased activity as gas clouds or disrupted stars fall into its gravitational well. When material accretes onto a black hole, it forms a hot, luminous disk that can outshine the surrounding stars, creating an active galactic nucleus. While Milky-Meda's relatively gas-poor environment makes sustained activity unlikely, occasional feeding events might temporarily awaken the central black hole, causing flares of radiation across the electromagnetic spectrum. These occasional bursts of activity, whether in star formation or black hole accretion, will become increasingly rare as Milky-Meda ages. The merged galaxy will gradually settle into the characteristic behavior of massive ellipticals throughout the universe's relatively featureless systems, dominated by old stellar populations and containing little cold gas. This galactic senescence represents the natural evolution of systems formed through major mergers, their wild youth of rapid star formation and active growth, giving way to a more sedate middle and old age. As we contemplate the birth and evolution of Milky-Meda, we gain perspective on the life cycles of galaxies. Like stars, galaxies follow evolutionary paths shaped by their initial conditions and subsequent interactions. The Milky Way and Andromeda, born as separate systems in the early universe, developed as spiral galaxies rich in gas and ongoing star formation. Their approaching collision will transform them into a single elliptical system, fundamentally different in structure and behavior from either parent. This transformation represents not an end, but a metamorphosis, a new chapter in the ongoing story of matter's organization in our cosmic neighborhood. From two spirals, one calm, glowing galaxy emerges. Even this dimming, aging galaxy will not represent the final state of the local group. On much longer timescales, perhaps trillions of years, even the longest-lived stars will eventually exhaust their fuel. Red dwarfs, despite their miserly use of hydrogen, will eventually convert enough of their mass to helium to destabilize their fusion reactions. One by one, these stellar embers will fade to become black dwarfs, dark objects composed primarily of carbon and oxygen, no longer generating energy through nuclear fusion. As stars die without replacement, the consolidated galaxy will grow increasingly dark. Stellar remnants, white dwarfs, neutron stars, and black holes will dominate its mass, with only a dwindling population of red dwarfs still shining. The once bright galaxy will become a ghostly collection of dark objects orbiting a central black hole, their presence detectable primarily through rare gravitational interactions, rather than electromagnetic radiation. During this extended period of stellar extinction, another process will operate on the galaxy's structure: relaxation. Through countless gravitational interactions, stars and stellar remnants will gradually exchange energy, with some gaining speed and others slowing down. This process, operating over timescales of quadrillions to quintillions of years, will cause some objects to spiral inward toward the galactic center, potentially feeding the central black hole, while others gain enough energy to escape the galaxy entirely, becoming intergalactic wanderers in the expanding cosmic void. The central supermassive black hole, formed from the merged black holes of the Milky Way, Andromeda, and potentially other galaxies of the local group, will play a crucial role in this late-stage evolution. As stellar remnants occasionally pass close to this gravitational monster, some will be captured and consumed, converting their mass to energy through accretion. Others will be flung outward through gravitational slingshot effects, potentially achieving escape velocity from the galaxy. Through these processes, the central black hole will gradually grow while the surrounding galaxy loses mass, shifting the balance of power at the heart of the former local group. Eventually, after timescales almost beyond comprehension perhaps, 10 to the 100th power year 7, black holes will evaporate through a quantum process called Hawking radiation, where particle-antiparticle pairs created near the event horizon lead to a gradual loss of mass. The central supermassive black hole, with a mass potentially billions of times that of our Sun, would be the last to go, persisting for an unimaginable duration before finally dissolving into radiation, leaving behind no structured matter where once a vibrant group of galaxies existed. This ultimate fate, the complete dissolution of all structure through quantum processes, lies so far in the future that it approaches the realm of philosophical speculation rather than testable science. Long before such final states are reached, other physical processes, perhaps yet undiscovered, might intervene to change the universe's evolution. The frontiers of physics continue to advance, and our understanding of the universe's ultimate fate remains tentative, a scientific story still being written. As we contemplate these vast timescales and the eventual fate of our galactic neighborhood, we gain perspective on our moment in cosmic history. We exist during a relatively early phase of the universe, approximately 14 billion years after the Big Bang, in a cosmos that may persist in recognizable form for trillions of years to come. We inhabit the universe while it remains dynamic and evolving, filled with active galaxies, forming stars from abundant gas. Future observers, trillions of years hence, would inhabit a markedly different cosmos, darker, redder, more isolated, its structures aging toward eventual extinction. This perspective on cosmic timescales also illuminates the significance of the approaching Milky Way-Andromeda merger. While dramatic from our perspective, this collision represents just one step in the local group's long evolutionary significant restructuring, but not a final state. The merged Andromeda Galaxy will itself continue to evolve, absorbing smaller satellites, experiencing stellar birth and death, and gradually transforming as the universe around it changes. The collision marks not an end, but a transition, one chapter in an ongoing cosmic story. The local group's evolution also reminds us of the hierarchical nature of cosmic structure. Individual stars form families called galaxies. Galaxies form associations called groups and clusters. These in turn form superclusters, which themselves trace the vast cosmic web that spans the observable universe. At each level, gravity works to consolidate structure, drawing components together despite the universe's overall expansion. The approaching merger of the Milky Way and Andromeda, followed by the local group's gradual consolidation, exemplifies this universal tendency toward gravitational assembly, counterbalanced only by the mysterious dark energy driving cosmic expansion. As we observe distant galaxy clusters with our most powerful telescopes, we see structures at various stages of this evolutionary process. Some remain loose associations of distinct galaxies, others show active mergers in progress, and still others have largely consolidated into one or two dominant systems surrounded by a dwindling collection of satellites. This diversity of states, observable across billions of light years, allows astronomers to piece together the likely sequence of events awaiting our own local group, reading our future in the present state of more evolved systems. The fate of the local group also carries implications for the long-term survival of life and intelligence in our cosmic neighborhood. The consolidation of the group into a single, aging galaxy, followed by the recession of all external systems beyond the cosmic horizon, would fundamentally constrain the resources available to any surviving civilizations. The depletion of gas would limit star formation, gradually reducing the available energy as existing stars die without replacement. And the isolation caused by accelerating cosmic expansion would prevent exploration or resource utilization beyond the former local group's boundaries. Any intelligence surviving into this distant era would face the challenge of adapting to an increasingly cold, dark, resource-limited environment. The vibrant cosmic ecosystem that currently surrounds us with its diverse galaxies and abundant energy from active stars, would give way to a more constrained reality. This transition from cosmic abundance to scarcity represents perhaps the ultimate environmental challenge for the long-term survival of life in any form. Despite this seemingly bleak ultimate fate, the timescales involved are so vast as to defy human comprehension. The local group will remain a dynamic, evolving system for trillions of years to come, with abundant resources and energy available throughout this extended period. Countless generations of stars will form and die, perhaps nurturing countless forms of life on their attendant planets, before the final decline into darkness. The universe may grow cold in its distant future, but its middle age will be long and potentially fruitful. Throughout our cosmic journey from the Milky Way to Andromeda, two fundamental forces have shaped our narrative: gravity and time. Gravity draws galaxies together across vast distances, orchestrating their dance through space. Time provides the stage upon which this dance unfolds, stretching the cosmic drama across billions of years. Tonight, we explore how these twin forces govern not only the approaching collision between galactic giants, but the ultimate fate of stars and galaxies throughout the universe. Gravity stands as perhaps the most familiar yet mysterious of nature's fundamental forces. We experience it constantly as the pull that keeps us bound to Earth's surface. Yet this same force, operating across cosmic distances, holds galaxies together, guides their motion through space, and will eventually bring the Milky Way and Andromeda together in a transformative collision. Despite its apparent weakness compared to other fundamental force, electromagnetism is approximately 10 to the 40 power times. Stronger gravity dominates the large-scale structure and evolution of the universe, precisely because it always attracts and never repels. This universally attractive nature of gravity creates a cumulative effect across cosmic scales. While the gravitational attraction between individual stars is typically too weak to significantly influence their motion, the combined gravitational field of hundreds of billions of stars creates galaxies' vast, stable structures that persist for billions of years. Similarly, the mutual gravitational attraction between neighboring galaxies forms groups and clusters cosmic neighborhoods, bound together by invisible threads of gravitational influence. The approaching collision between the Milky Way and Andromeda exemplifies gravity's patient power. Despite being separated by 2.5 million light-years, these galaxies feel each other's gravitational pull. This attraction, operating over billions of years, gradually alters their velocities, drawing them inexorably closer. What appears from a human perspective as an enormously slow process, the galaxies approaching at approximately 110 kilometers per second becomes inevitable when multiplied by cosmic timeframes, with gravity's gentle but persistent pull ensuring their eventual merger. Gravity operates through the geometry of space-time itself. According to Einstein's general theory of relativity, mass and energy curve the fabric of space-time, and this curvature guides the motion of objects through space. The Milky Way and Andromeda each create significant distortions in space-time, and their mutual influence shapes the path they follow toward each other. This curved space understanding of gravity reveals that the galaxies are not so much attracted to each other as following the natural contours of a space-time shaped by their combined presence. While gravity draws the galaxies together, their collision unfolds across timescales that challenge human comprehension. The approach and merger will span billions of years of duration, thousands of times longer than human civilization has existed. Even the most catastrophic seeming cosmic events proceed with a stately grace when viewed from the perspective of human lifetimes. A single human life of 100 years would witness the galaxies drawing closer by just 3.5 billion kilometers about. The distance from the Sunday to Uranus, barely perceptible change in their separation. This vast disparity between human and cosmic timescales shapes our understanding of galactic evolution. We cannot observe the complete merger of any galaxy pair, from initial approach to final coalescence, within a human lifetime, or even the entire span of recorded history. Instead, astronomers piece together the story by observing different galaxy pairs at various stages of merger throughout the universe, creating a composite picture of the process. Each observed pair becomes a snapshot in an album that, when arranged in sequence, reveals the likely future of our own galactic neighborhood. The patience required to comprehend cosmic timescales reflects a fundamental truth about the universe. Its most significant transformations occur gradually, through the accumulation of small changes over enormous periods. The collision of galaxies, the evolution of stars, the formation of planetary systems all unfold across timeframes that dwarf human experience. This gradual nature of cosmic change provides stability for systems like our solar system, allowing the development of complex phenomena like life, while simultaneously ensuring the universe remains in a constant state of evolution and transformation. Time's arrow points in a single direction, from past to future, carrying galaxies toward their destined encounters. This unidirectional flow emerges from the universe's fundamental physics, particularly the second law of thermodynamics, which states that the overall disorder or entropy of a closed system always increases over time. The merger of the Milky Way and Andromeda represents a local decrease in entropy, creating a more organized, consolidated structure. But this organization comes at the cost of increased entropy elsewhere, as energy dissipates through processes like gravitational radiation and heat generation during gas cloud collisions. This thermodynamic perspective on cosmic evolution reveals a tension at the heart of the universe's development. Gravity tends to draw matter together, creating increasingly concentrated structures from stars to galaxy clusters. Yet the second law of thermodynamics ensures that disorder increases overall, with stars eventually exhausting their fuel and galaxies gradually losing their distinctive structures. The universe exists in a balance between these competing tendencies: organization through gravity versus disorganization through entropy, with the latter guaranteed to prevail in the most distant future. The stars themselves, the fundamental building blocks of galaxies, exist in a similar tension between gravity and time. A star forms when gravity compresses a cloud of hydrogen gas until its core becomes dense and hot enough to ignite nuclear fusion. This fusion generates an outward pressure that counterbalances gravity's inward pull, creating a stable, self-regulating system that can persist for billions or even trillions of years. Yet time ensures this balance is temporary. Eventually, the star exhausts its nuclear fuel, and gravity reclaims dominance, compressing the stellar remnant into a white dwarf, neutron star, or black hole. The stellar populations of the Milky Way and Andromeda embody this interplay between gravity and time. Both galaxies contain stars at various stages of this cosmic life cycle. Bright blue stars burn their fuel rapidly, lasting only millions of years before exploding as supernovae. Yellow stars, like our Sun, persist more modestly for billions of years. Tiny red dwarfs, the most common stars in both galaxies, burn their fuel so slowly they may shine for trillions of years. And scattered throughout both galaxies are the remnants of stars, long dead white dwarfs, neutron stars, and black hole objects where gravity has finally overcome nuclear fusion's resistance. When the Milky Way and Andromeda merge, their combined stellar populations will continue this evolutionary journey. The collision itself will trigger new star formation as gas clouds compress, temporarily increasing the number of bright, short-lived stars. But over the longer term, as the merged galaxy depletes its gas reserves, star formation will decline. The bright stars will burn out without replacement, leaving the galaxy increasingly populated by long-lived red dwarfs and stellar remnants. Gravity's patient work of stellar birth and death will continue, but with diminishing raw materials for creating new stars. The collision will also accelerate another aspect of gravity's work: the growth of the galaxy's central black holes. Both the Milky Way and Andromeda harbor supermassive black holes at their center subjects, where gravity has so completely dominated other forces that not even light can escape their gravitational pull. The Milky Way's central black hole, Sagittarius A star, contains approximately 4 million solar masses. Andromeda's central black hole is substantially larger, estimated at 100 to 200 million solar masses. As the galaxies merge, these black holes will eventually find each other and form a binary system, orbiting their common center of mass. Gravitational interactions with surrounding stars will gradually draw them closer until they enter the regime where gravitational waves ripples in space-time predicted by Einstein's theory of relativity carry away their orbital energy. This emission of gravitational waves will cause the black holes to spiral together and ultimately merge, releasing an enormous amount of energy in a form invisible to conventional telescopes, but potentially detectable by future gravitational wave observatories. The merger of these supermassive black holes represents gravity's ultimate triumph, the union of two regions where space-time is already dramatically curved into a single entity with even stronger gravitational influence. The resulting black hole, containing hundreds of millions of solar masses, will sit at the heart of the merged galaxy, gradually accreting additional matter and potentially growing to become one of the most massive black holes in the local universe over the subsequent billions of years. Beyond the central black holes, gravity's influence extends throughout both galaxies in the form of dark matter, an invisible substance that reveals itself only through its gravitational effects. Both the Milky Way and Andromeda are embedded within extensive halos of dark matter that contain the majority of their total mass. These halos, extending far beyond the visible galaxies, establish the gravitational foundation upon which the visible structures rest. During the merger, these dark matter halos will interact and combine, forming a single, roughly spherical distribution centered on the merged galaxy. This process occurs somewhat differently than the merger of the visible galaxies, as dark matter particles interact only through gravity, passing through each other without the direct collisions that affect gas clouds. The combined dark matter halo will establish the gravitational potential of the merged galaxy, influencing the orbits of stars throughout the system and contributing to its transformation from a spiral to an elliptical structure. Time plays a crucial role in this transformation as well. The distinct spiral structures of the Milky Way and Andromeda persist because their stars orbit the galactic centers in an organized fashion, completing a full circuit approximately every 230 million years near the Sun's position. This organized rotation creates and maintains the spiral pattern. During the merger, gravitational interactions will scatter stars into more random orbits, a process that requires hundreds of millions of years to thoroughly mix the stellar populations. The resulting elliptical galaxy forms not in an instant, but through the gradual randomization of stellar orbits over an extended period. This transformation reflects a fundamental aspect of gravity's influence across cosmic time. It converts ordered kinetic energy into random motion. The rotating disks of spiral galaxies represent highly ordered systems, with most stars moving in the same direction within a relatively flat plane. As these galaxies interact gravitationally, this ordered motion gradually converts to random velocities in 3 dimensions. While the total energy and angular momentum remain conserved, their distribution changes fundamentally, transforming the galaxy's structure and appearance. Beyond the merger of individual galaxies, gravity and time shape the evolution of entire cosmic structures. The local group, currently containing more than 50 galaxies bound together by gravity, will eventually consolidate into a single massive galaxy, as dynamical friction, gravitational drag experienced by objects moving through a field of stars causes satellite galaxies to spiral inward and merge with the central system. This process, unfolding over hundreds of billions of years, represents gravity's patient work of cosmic assembly, drawing scattered matter into increasingly concentrated structures despite the universe's overall expansion. This consolidation occurs within the context of an expanding universe, creating a tension between gravity's attractive pull and the universe's tendency to carry galaxies apart. Currently, the expansion of space itself causes most distant galaxies to recede from us at velocities proportional to their distance, a relationship known as Hubble's law. This expansion, apparently accelerating due to the influence of dark energy, will eventually carry all galaxies beyond the local group, beyond our cosmic horizon, making them permanently unobservable to astronomers in our region. The eventual isolation of the consolidated local group represents one of time's most profound effects on cosmic structure. In the distant future, perhaps 100 billion years from now, astronomers in our galactic neighborhood would observe an apparently empty universe, beyond the local system. All evidence of the vast cosmic web of galaxies, galaxy clusters, and superclusters would have disappeared from view, carried beyond detection by the universe's relentless expansion. The accumulated light travel time would exceed the age of the universe itself, rendering these distant structures not merely invisible, but fundamentally unobservable. Within this isolated island of the former local group, stellar evolution will continue its inexorable process. Stars form, live, and die according to their initial mass, with the most massive exhausting their fuel in millions of years, and the least massive potentially shining for trillions. This stellar life cycle, driven by the balance between gravity and nuclear fusion, will gradually deplete the gas reserves of the consolidated galaxy, leaving it populated primarily by low-mass stars and stellar remnants, the cooling embers of once bright suns. On the longest timescales, perhaps trillions to quadrillions of years, even the most miserly stars will exhaust their nuclear fuel. Red dwarf stars, which can shine for up to 10 trillion years due to their low mass and correspondingly slow rate of fusion, will eventually convert enough hydrogen to helium to destabilize their internal balance. One by one, these stellar embers will fade to become black dwarfs gold, dark objects composed primarily of carbon and oxygen, no longer generating energy through nuclear fusion. As stars die without replacement, the consolidated galaxy will grow increasingly dark and cold. Stellar remnants, white dwarfs, neutron stars, and black holes will dominate its mass, with only a dwindling population of red dwarfs still shining. The galaxy, once brilliantly illuminated by hundreds of billions of stars, will become a ghostly collection of dark objects orbiting a central supermassive black hole, their presence detectable primarily through rare gravitational interactions rather than electromagnetic radiation. Even these stellar remnants are not eternal. White dwarfs and neutron stars will gradually cool, their temperatures approaching that of the background universe over inconceivably long periods. Black holes, once thought to be permanent features of the cosmos, will eventually evaporate through Hawking radiation, a quantum process where particle-antiparticle pairs created near the event horizon lead to a gradual loss of mass. This process operates extremely slowly for stellar mass black holes and even more glacially for supermassive ones, with estimated lifetimes up to 10 to the 100th power years for the largest examples. The ultimate fate of matter in a universe dominated by dark energy appears to be complete dissolution. As black holes evaporate, stars cool, and protons potentially decay through processes not yet confirmed by particle physics, all structured matter would eventually disappear, leaving only a diffuse sea of elementary particles separated by ever-increasing distances as space continues to expand. This heat death scenario represents the final triumph of entropy over gravity, with the organized structures created by gravitational assembly eventually succumbing to disorder and dissolution. This vision of the universe's far future remains speculative, based on extrapolating current physical understanding to timeframes and conditions far beyond direct observation. New physics, currently unknown, might significantly alter this projection. Proton decay might not occur, allowing stable matter to persist indefinitely. Dark energy's properties might change over time, potentially halting or even reversing cosmic acceleration. Quantum gravity effects, still not fully understood, might introduce entirely new phenomena at extremely low temperatures or over extremely long timescales. Despite these uncertainties about the universe's ultimate fate, the approaching collision between the Milky Way and Andromeda stands on firmer ground, representing a predictable consequence of gravity's influence over billions of years. This cosmic encounter, while distant from human timescales, connects us to the larger rhythms of galactic evolution. The stars we see tonight exist within structures shaped by gravity over cosmic time, destined for transformation in a future beyond human experience, but nonetheless real and inevitable. As we contemplate these vast processes, we gain perspective on our place in cosmic history. We live during a relatively early phase of the universe, when galaxies remain distinctly separated, actively forming stars from abundant gas. Future observers, trillions of years hence, would inhabit a markedly different cosmos, darker, emptier, its structures aging toward eventual extinction. Our moment allows us to observe the universe while it remains dynamic and diverse, its history still accessible through the light of distant galaxies not yet carried beyond our cosmic horizon. The stars will forget, but the motion that made them will remain. Beyond the local group, beyond the Virgo supercluster, extends a structure of almost incomprehensible scale and beauty, the cosmic web. This vast network of filaments, clusters, and voids forms the largest known structure in the universe, spanning billions of light years and connecting galaxies across cosmic distances. Tonight, we explore how the approaching collision between the Milky Way and Andromeda fits into this grander cosmic tapestry, and how similar mergers throughout the universe shape the evolution of structure on the largest scales. The cosmic web, revealed by modern astronomical surveys, presents a universe organized like a sponge or foam, with galaxies concentrated along filaments and sheets that surround vast, nearly empty voids. These filaments intersect at dense nodesta locations of galaxy clusters and superclusters. This pattern, emerging from the interaction between gravity and the universe's expansion, creates a cosmic architecture, both ordered and organic, with structures echoing one another across different scales. Our local group occupies a relatively quiet region of this cosmic web, positioned along a filament extending from the Virgo cluster, the nearest substantial galaxy cluster, at approximately 53 million light-years distant. This filament, part of the larger Virgo supercluster, gently guides the motion of the local group through space, influencing the approach of the Milky Way and Andromeda through its extended gravitational field. The collision we anticipate represents not an isolated event, but one thread in a vast tapestry of galactic interactions occurring throughout the cosmic web. Throughout this enormous structure, galaxy mergers, similar to the approaching Milky Way-Andromeda collision, occur constantly. In dense galaxy clusters like Virgo or Coma, such interactions happen more frequently due to the higher concentration of galaxies in a relatively confined space. In these cosmic metropolises, galaxies experience a more chaotic environment than the relatively sedate local group, with multiple gravitational influences tugging them in different directions and increasing the probability of encounters and mergers. Across the observable universe, astronomers estimate that approximately 1% of galaxies are currently undergoing major mergers, collisions between galaxies of comparable mass. Another 5 to 10% show signs of recent merger activity or minor mergers with smaller companions. These percentages translate to billions of ongoing galactic collisions throughout the cosmos, making such events common in the universe, while remaining rare within the lifetime of a single observer or civilization. These countless mergers occurring across the cosmic web drive a fundamental transformation in galactic populations over cosmic time. In the early universe, observed through telescopes that peer billions of light years into space and thus billions of years into the past, spiral galaxies dominated the cosmic landscape. These gas-rich, actively star-forming systems represented the youthful phase of galactic evolution. As the universe aged, mergers gradually converted many of these spirals into elliptical galaxies, gas-poor, spheroidal systems composed primarily of older stars. This transformation, from a universe dominated by spirals to one with an increasing proportion of ellipticals, represents one of the most significant evolutionary trends in cosmic structure. The Milky Way-Andromeda merger, creating the elliptical galaxy Milkomeda, exemplifies this broader pattern. What we anticipate in our cosmic neighborhood has already occurred countless times throughout the universe, each merger converting actively star-forming spirals into more quiescent ellipticals. These mergers leave observable signatures that astronomers can detect across vast distances. When galaxies collide, the compression of gas clouds triggers bursts of star formation, far exceeding the normal rate in undisturbed galaxies. These starbursts produce large numbers of massive luminous stars that burn brightly but briefly, making the merging system temporarily more luminous, particularly in ultraviolet and blue wavelengths. By identifying galaxies with these characteristic emission patterns, astronomers can recognize ongoing mergers even when the individual galaxies cannot be clearly resolved. More dramatic still are the effects when merging galaxies contain substantial amounts of gas and dust that feed their central black holes. As this material spirals inward toward the black hole, it forms an accretion disk heated to millions of degrees, generating enormous amounts of radiation across the electromagnetic spectrum. These active galactic nuclei, or AGN, can temporarily outshine their entire host galaxies, creating quasars visible across billions of light years. The most luminous objects in the universe, quasars represent the most energetic phase of galaxy mergers. The Milky Way-Andromeda collision, while significant in our cosmic neighborhood, will likely produce neither a powerful starburst nor a luminous quasar. Both galaxies have already converted much of their original gas into stars, leaving relatively modest reserves for collision-induced star formation. Their central black holes, while massive, currently accrete matter at low rates, and the merger is unlikely to channel enough gas to their vicinity to create a true quasar. The collision will be spectacular when viewed from within, but relatively modest when compared to the most energetic mergers occurring elsewhere in the cosmic web. This variation in merger outcomes reflects the diversity of conditions throughout the cosmic web. In regions where galaxies still retain substantial gas reserves, mergers trigger spectacular starbursts and potentially feed luminous quasars. In more evolved regions, where galaxies have already converted much of their gas to stars, mergers proceed more quietly, primarily rearranging existing stars rather than triggering extensive new star formation. The approaching Milky Way-Andromeda collision falls closer to this latter category, reflecting the relatively mature state of both galaxies. The cosmic web itself evolves over time, shaped by these countless mergers and the overall expansion of the universe. In the early cosmos, the web consisted of smaller, more numerous filaments connecting relatively small protogalaxies. As gravity drew matter together along these filaments, larger structures formed at their intersections, gradually building the galaxy clusters and superclusters we observe today. This hierarchical growth, from small structures to progressively larger ones, represents the fundamental pattern of cosmic evolution under gravity's influence. Dark matter plays a crucial role in this evolutionary process. Comprising approximately 85% of all matter in the universe, dark matter forms the gravitational scaffold upon which the cosmic web is built. Computer simulations reveal that dark matter formed filamentary structures early in cosmic history, with ordinary visible matter following this underlying distribution. The approaching collision between the Milky Way and Andromeda thus represents not just the merger of their visible components, but the coalescence of their extensive dark matter halos, which established the gravitational pathways guiding their approach. The distribution of dark matter throughout the cosmic web influences the frequency and character of galaxy mergers. Regions with higher dark matter density naturally develop more concentrated galaxy populations, increasing the probability of interactions and mergers. The most massive galaxy clusters, located at the nodes where multiple filaments intersect, contain thousands of galaxies in relatively close proximity, creating environments where mergers occur much more frequently than in less dense regions like our local group. These variations in merger frequency across the cosmic web create a form of environmental evolution, where a galaxy's development depends not just on its internal properties, but on its cosmic location. Galaxies in dense clusters typically experience more mergers, converting to elliptical forms earlier in cosmic history. Galaxies in less dense regions, like the Milky Way and Andromeda, may retain their spiral structure longer, experiencing major mergers later or not at all. This environmental influence adds another dimension to galactic evolution, complementing the internal processes of star formation and stellar aging. The approaching collision between the Milky Way and Andromeda reflects this environmental context. The local group represents a relatively low-density region of the cosmic web, containing only a few dozen significant galaxies spread across 10 million light-years. The Milky Way and Andromeda, as the group's dominant members, naturally gravitational toward each other but have had sufficient isolation to maintain their spiral structures for billions of years. Their impending merger, while inevitable under gravity's influence, has been delayed by the relatively diffuse nature of their cosmic neighborhood. Beyond our local group, Similar processes operate throughout the cosmic web, but at varying rates and with different outcomes depending on local conditions. In dense galaxy clusters, most large spirals have already transformed into ellipticals through multiple mergers. In void regions, where galaxies are exceedingly rare, spirals may persist indefinitely, never encountering a comparable galaxy with which to merge. Between these extremes lie a spectrum of environments, each shaping the evolutionary paths of its constituent galaxies through the frequency and nature of interactions. This sustained diversity ensures that the cosmic web remains a vibrant, evolving structure even as it ages. The universe exists not as a homogeneous system evolving uniformly, but as a tapestry of varied environments, following different evolutionary paths. The approaching collision between the Milky Way and Andromeda represents just one thread in this tapestry. Its particular character, shaped by the specific properties of the interacting galaxies and their local cosmic environment. As we contemplate the cosmic web in its entirety, we gain perspective on our place within its vast structure. The Milky Way and Andromeda, while among the largest galaxies in the local group, represent moderate-sized systems within the broader cosmic context. The most massive galaxies in the universe, typically ellipticals at the centers of rich galaxy clusters, contain tens of trillions of stars more than the combined stellar populations of the Milky Way and Andromeda. Our galaxies, while substantial, exist as middle-class citizens in the cosmic hierarchy. This perspective extends to the approaching collision itself. While revolutionary for our galactic neighborhood, the Milky Way-Andromeda merger represents a relatively modest event on the cosmic scale. Throughout the universe, more spectacular collisions occur between larger galaxies or between multiple systems simultaneously. The most dramatic mergers, typically occurring at the centers of rich galaxy clusters, can involve dozens of galaxies in a complex gravitational ballet, creating massive elliptical galaxies that dwarf what Milkomeda will become. Yet despite its relative modesty in the cosmic context, the approaching collision holds special significance as the merger that will transform our cosmic home. For any observers existing in the local group billions of years hence, the formation of Milkomeda will represent a fundamental restructuring of their galactic environment, altering the appearance of the night sky and the distribution of stars and gas throughout their observable universe. Its significance lies not in its absolute scale, but in its relevance to our particular cosmic neighborhood. This perspective, balancing the cosmic commonplace with the locally significant, characterizes much of modern astronomy. Throughout the universe, processes similar to those occurring in our cosmic vicinity operate continuously. Stars form and die. Galaxies interact and merge. Black holes accrete matter and occasionally combine. What makes these processes significant is not their uniqueness, but their relevance to specific cosmic localities and the observers who inhabit them. As we expand our view to encompass the entire cosmic web, this balance between universal processes and local significance becomes increasingly apparent. The approaching collision between the Milky Way and Andromeda exemplifies patterns occurring throughout the cosmos, while simultaneously representing a uniquely important event for our galactic neighborhood. Its study connects us to both the universal patterns of cosmic evolution and the particular history of our local environment. This connection between the universal and the particular underlies much of our cosmic understanding. The laws of physics that govern the Milky Way-Andromeda collision operate identically throughout the universe, creating similar outcomes under similar conditions across billions of light years. Yet the specific expression of these laws in each galaxy pair depends on their particular properties and cosmic context, creating a universe that is simultaneously governed by universal principles and expressed through endless, unique variations. The cosmic web itself embodies this interplay between universal patterns and particular expressions. Its basic structure, filaments connecting nodes surrounding voids, appears similar across the observable universe. Yet no two filaments are identical. No two clusters contain exactly the same galaxy populations, and no two voids have precisely the same dimensions. The universe follows consistent patterns while never exactly repeating itself, creating a cosmic tapestry of infinite variation within recognizable themes. As we return our focus to the approaching collision between the Milky Way and Andromeda, we carry this broader perspective with us. The merger we anticipate connects to patterns operating throughout the cosmic web, while representing a unique event with specific characteristics determined by the particular properties of our local galaxies. Its study offers insights into both universal processes of galactic evolution and the specific future awaiting our cosmic neighborhood. As our cosmic journey draws to a close, we return to where we began, contemplating two spiral galaxies floating in space, separated by silence, yet bound by gravity's invisible threads. The Milky Way and Andromeda, cosmic neighbors for billions of years, approach their shared destiny with the patience that only celestial objects can possess. Their coming merger, unfolding across timeframes that dwarf human existence, represents not an ending, but a transformation, cosmic metamorphosis that will reshape our galactic neighborhood. The story we've traced tonight spans scales that challenge human comprehension, from the motion of individual stars to the collision of galaxy clusters, from timeframes measured in human lifetimes to those counted in billions of years. Throughout this vast narrative, certain themes emerge with striking clarity. The patient power of gravity, drawing matter together across cosmic distances. The inexorable flow of time transforming galaxies through stellar birth and death, and the beautiful complexity that emerges when physical laws operate across the enormity of space. Gravity, perhaps the weakest of nature's fundamental forces, yet the most far-reaching, orchestrates this cosmic dance. Despite being separated by 2.5 million light-years, the Milky Way and Andromeda feel each other's gravitational pull. This attraction, operating over billions of years, gradually alters their velocities, drawing them inexorably closer. What appears from a human perspective as an enormously slow process becomes inevitable when multiplied by cosmic timeframes, with gravity's gentle but persistent pull ensuring their eventual merger. Time provides the stage upon which this gravitational drama unfolds. The approach and merger will span billions of years, a duration thousands of times longer than human civilization has existed. Even the most catastrophic seeming cosmic events proceed with a stately grace when viewed from the perspective of human lifetimes. A single human life of 100 years would witness the galaxies drawing closer by just 3.5 billion kilometers, a barely perceptible change in their separation. Yet within this slow cosmic ballet, faster rhythms play out simultaneously. Stars orbit their galactic centers, completing a circuit every few hundred million years. New stars form from compressed gas clouds over periods of millions of years. Massive stars live brief, brilliant lives spanning only millions of years before exploding as supernovae. And throughout these varied timescales, light travels between the galaxies, crossing the intervening void in 2.5 million years. A journey begun when early humans were just learning to use stone tools. The collision itself, despite the term's violent connotations, will unfold as a graceful dance of stars and gas. Unlike collisions between solid objects, galactic mergers occur primarily through gravitational interactions, rather than direct impacts. Stars will pass by each other like ships in the night, their courses altered by gravity, but rarely resulting in direct collisions. Gas clouds will compress, triggering bursts of star formation that illuminate the merging galaxies with the light of newly born stars. And throughout this process, the galaxies will gradually lose their distinctive spiral identities, transforming into a single elliptical system that bears little resemblance to either parent. This transformation from two spiral galaxies to one elliptical represents a fundamental change in galactic character. Spiral galaxies like the Milky Way and Andromeda embody cosmic youth, actively forming stars, rich in gas and dust, their structures dynamically maintained through organized rotation. The elliptical galaxy that will form from their merger represents a more mature phase, predominantly older stars, less active star formation, a more randomized stellar distribution. This transition from youth to maturity echoes patterns occurring throughout the cosmos as galaxies evolve through interactions and internal processes. For any observers existing in our solar system during this extended merger, the night sky would transform beyond recognition. The familiar band of the Milky Way would distort and eventually be joined by the approaching spiral of Andromeda, gradually expanding across the heavens until it dominates the nighttime view. As the merger progresses, these distinct patterns would blur and merge, eventually forming a more diffuse, uniform distribution of stars, visible in all directions. The night sky, humanity's first and most enduring astronomical observatory, would display a cosmic transformation unfolding in slow motion across hundreds of human generations. The Earth itself, if it still exists, would likely survive this cosmic collision, physically unscathed. The vast distances between stars ensure that direct stellar collisions remain extremely rare, even during galaxy mergers. Our solar system, currently orbiting approximately 26,000 light-years from the Milky Way's center, would experience the merger primarily as a gravitational perturbation, potentially throwing it into a new orbit around the merged galaxy's center. Any life that might still exist on Earth would witness a transformed sky, but would likely face greater challenges from the Sun's natural evolution than from the galactic collision occurring simultaneously. This cosmic perspective, spanning billions of years and millions of light-years, reminds us of our place in the universe's ongoing story. The approaching collision between the Milky Way and Andromeda will occur long after current human civilization has passed into history. The stars we see tonight will have completed multiple orbits around the galaxy, many reaching the ends of their lifespans and being replaced by new generations. The Earth itself will have changed profoundly through natural processes and whatever influence future intelligent life might exert upon it. Yet the basic physical laws we've explored tonight will continue to operate, guiding the merger with the same patience and precision they exhibit in the cosmos we observe today. As we contemplate this distant future, we're reminded of the transient nature of all cosmic structures. The familiar spiral arms of the Milky Way, the constellations that have guided human navigation and inspired mythology, the very galaxy we call home, represent temporary patterns in a universe of perpetual change. The stars will continue their cosmic journeys long after their current configurations have dissolved, participating in new structures shaped by gravity's enduring influence. The matter and energy that constitute our current cosmic neighborhood will persist, rearranged into new forms, but continuing their ancient dance through space and time. This perspective grants both humility and wonder. Humility, as we recognize the brevity of human existence compared to cosmic timescales. Wonder, as we comprehend the magnificent processes unfolding across the universe, accessible to human understanding, despite their vastness. We exist in a universe both comprehensible through scientific inquiry and awe-inspiring in its scale and complexity, a cosmos whose basic principles we can grasp, even as its full majesty exceeds our direct experience. We live in a galaxy made of light, and we are moving toward another. Slowly, gently, over billions of years, two worlds become one. Sleep now, and let the stars guide you home from the Milky Way to Andromeda.